In this presentation we discuss the kinematics of rigid bodies with the following content. We will start with the basic definitions characterizing the position of rigid bodies and describe their special motions. Although forces applied on bodies are the topic of dynamics, we need talk about the principle of superposition of forces acting on rigid bodies, since the description of motion of non-point-like objects under the influence of forces is more complicated than the one of the motion of point masses. We will introduce the quantity called torque related to the rotations of rigid bodies, and we then present how to reduce a system of forces exerted on a rigid body with the help of the torque produced by these forces. We also define the centroid and the center of mass of rigid bodies, which is a useful concept in the study the effect of forces applied on a rigid body. By using this formalism, we can study the equilibrium of rigid bodies and the stability of the equilibrium state, and describe the condition for equilibrium. We introduce the principle of virtual work as well and reformulate the criterion of equilibrium for rigid bodies with the help of this principle. Finally, we present simple machines and weighing scales operating on the principles related to the criterion of equilibrium for rigid bodies. In order to start with the procedure to determine the position of a rigid body, we recall the concept of rigid body. When we presented the models used to describe the bodies in mechanics, we defined rigid body as an idealized model where the points of the body cannot change their position with respect to each other. The position of a body is always determined with respect to a frame of reference, for example the laboratory where we perform experiments with the body, and we describe its position in a coordinate system attached to the frame of reference. The position of a rigid body is completely determined in the three-dimensional space by specifying the positions of three arbitrary points A, B, and C of the body, provided they are not collinear, that is, these points are not lying on the same straight line. For if we fix only the point A of the body, then the points B and C can be rotated over the spheres of radii given by the distances of the points B and C from the point A, and with the center at the point A. If the point B of the body is also fixed, then the point C can still be rotated about the axis passing through the points A and B. If we fix the 3 points A, B, and C of the body, then we fix the position of the whole body, that is, we completely specified its position in the space. Since we use three non-collinear points and the position of a point is described by three coordinates in a coordinate system, we need 3 times 3, that is 9 data to determine the position of a rigid body in the coordinate system attached to the frame of reference. If we use a Cartesian coordinate system, then these data consist of the Cartesian coordinates x, y, and z of the points A, B and C. By definition, the distance between any 2 points of a rigid body is always the same even if the body moves. We can apply the Pythagorean theorem to describe the distance between the points A and B, and we can write that the square of the difference between xa and xb, plus the square of the difference between ya and yb, plus the square of the difference between za and zb is equal to the square of the distance d between the points A and B. We have two other equations for the point pairs A and C, and the point pairs B and C as well. The distances between the point pairs and the right-hand side of the equations are constants, whereas the coordinates of the points are functions of time for a moving body. By virtue of these three relations between the Cartesian coordinates, from the 9 data describing the position of a rigid body only 6 are independent. Therefore, the instantaneous position of a rigid body performing an arbitrary motion is determined by 6 independent data. In other words, a freely moving rigid body has 6 degrees of freedom as opposed to a freely moving point mass which has only 3 degrees of freedom. We can choose the 3 coordinates of an arbitrary point of the body and 3 angles describing its orientation to specify the 6 independent data for a rigid body, where the angles are the so-called Euler angles. In order to describe the position of a rigid body in the coordinate system with the coordinates x, y, z and the origin O, we attach another Cartesian coordinate system with the coordinates x', y', z' and the origin O' to the body. As a result, if the position and the orientation of this coordinate system is known, then the position of the body is specified. Its position is given by the coordinates x null, y null and z null of the point O' in the coordinate system x, y and z. We need other 3 data to determine the relative orientation of the 2 coordinate systems. In this respect the positions of the origins O and O' are indifferent, and we can translate the coordinate system x, y, and z from the point O to the point O' without changing its orientation. Then the relative orientation of the 2 coordinate system is determined as follows. First we rotate the coordinate system counterclockwise about its z-axis by the angle psi. Then we rotate the coordinate system counterclockwise about its x-axis by the angle theta. In the last step, we rotate the coordinate system counterclockwise about its z'-axis by the angle phi such that the y and z axes are brought into the y' and z' axes. As a result, the Cartesian coordinates x null, y null, and z null of the origin O' of the coordinate system attached to the body, and the Euler angles theta, psi, and phi describing the directions of the coordinate axes specify the instantaneous position of a rigid body. After discussing how to specify the position of a rigid body, we will study the description of the change in its position, that is its motion in space. A rigid body can perform different kinds of motion, and one kind of its motion is called translation. During translation of a rigid body, all the points of a body simultaneously move along congruous curves parallel with each other. If the translation is performed along a straight line, then these curves are also straight line segments. As a result, every point of a rigid body has the same velocity at a given instant of time, and the orientation of the body does not change during its motion. In such a situation, we only need one arbitrary point of the body to describe the instantaneous position of the body. Another important type of motion of a rigid body is the rotation about an axis. When a rigid body rotates, its points lying on the rotation axis remain at rest, whereas the rest of its points move along arcs lying planes perpendicular to the axis. In this case, we need not only an arbitrary point of the rigid body but also the orientation of a coordinate system attached to the body to describe its instantaneous position. These figures illustrate the difference between translation and rotation. The circles represent the trajectories of the points A and B of a rigid body during its motion. In the case of translation along a circular path depicted in the left-hand side, both the circles have the same radius but their centers are different. A well-known example for such a translation is the motion of the cabins of a Ferris wheel. The right-hand side figure shows either a rotation of a rigid body, where the rotation axis does not pass through the body, or a composition of one translation and a rotation with a rotation axis passing through the body. A simple example for this type of motion is a model railway traveling on a continuous circular loop, or the Moon orbiting the Earth, since the Moon keeps the same face to us. Now we can assume that the general motion of a rigid body is a composition of a series of infinitesimal translations and rotations of the body. We will illustrate this statement with a simple example. Let the 3 points specifying the position of a rigid body be the 3 corner points A1, B1 and C1 of an equilateral triangle at the instant of time t1, and let this triangle have another position with the corners at the points A2, B2 and C2 at the instant of time t2. Here the letter D denotes the length of the sides of the equilateral triangle. We can translate the triangle from its original position to the new one along the vector pointing from the point A1 to the point A2. As a result, the point A1 is translated to the point A2, the point B1 is translated to the point B'1, and the point C1 is translated to the point C'1. The points B'1, C'1, B2, and C2 lie on the sphere of the radius d with the center at the point A2. Now we draw a line passing through the point A2 such that a rotation about the axis represented by the line brings the points B'1 and C'1 into the points B2 and C2. The angle and the direction of the rotation axis can be determined by applying geometric considerations. The figure in the right-hand side shows the triangle A2B2C2 at the instant of time t2, and the translated triangle A2B'1C'1. We can represent the two sides with the corner A2 of the later triangle by the vectors pointing from the corner A2 to the corners B'1 and C'1. These vectors span the plane P' of the triangle and their cross product is perpendicular to the plane, that is, it gives the normal vector of the plane P'. Similarly, the two sides with the corner A2 of the triangle A2B2C2 are represented by the vectors pointing from the corner A2 to the corners B2 and C2. These vectors also span the plane P of the triangle and their cross product is perpendicular to the plane, forming the normal vector of the plane P. If we map the triangle A2B'1C' onto the triangle A2B2C2 by rotating it about an axis passing through their common corner A2, then the rotation axis lies on the angle bisector of the rotation angle measured between the planes P and P' of the triangles. As a result, the rotation axis is the intersection of the two planes passing through the point A2, and the axis is perpendicular to the normal vectors of the planes P and P'. This means that the rotation axis is parallel to the cross product of the normal vectors, and the angle phi between the two planes of the triangles gives the rotation angle. Both the direction of the rotation axis and the rotation angle can be determined from the coordinates of the corners of the triangles. If we calculate the cross product of the vectors pointing from the corner A2 to the corners B'1 and C'1, then its magnitude can be written as the product of the magnitudes of the vectors times the sine of pi over 3, the angle between the sides of an equilateral triangle. Since the length of the sides of the triangle is given by d, the magnitude of the cross product is equal to d squared times the square root of 3 over 2. The magnitude of the cross product of the vectors pointing from the corner A2 to the corners B2 and C2 is also given by d squared times the square root of 3 over 2 because the triangles are congruous. This result helps us to determine the rotation angle if we calculate the dot product of the normal vectors of the planes P and P', which can be written as the product of the magnitudes of the two normals, times the cosine of the angle phi measured between them. By substituting the magnitudes of the two vectors into this equation, we obtain 3 over 4 times d to 4, times cosine phi. For given triangles, the coordinates of the points A2, B'1, C'1, B2 and C2 are known. Then the cross product of the plane's normals can be computed from the coordinates of the points. Similarly, the left-hand side of the scalar product of the plane's normals is determined by these coordinates. Since the length d is fixed for the triangles, we can express the cosine of the rotation angle as a function of the coordinates. We can also translate the triangle A1B1C1 along the vector pointing from the point B1 to the point B2 to the position described by the triangle A'1B2C'1. Then we need to rotate the later triangle about an axis passing through the point B2 to bring it to the position of the triangle A2B2C2. Although the translation vectors are different and the rotation axis passes through different corners of the triangles in the two cases, both the axes have the same directions and both the rotation angles are the same. It follows from the fact that the plane P'' of the triangle A'1B2C'1 is parallel with the plane P', and the intersection of the planes P and P'' is parallel to the intersection of the planes P and P'. As a result, the rotation axes of the two cases have the same direction. Similarly, the rotation angles are also the same because the angle measured between the planes P and P' is also equal to the angle between the planes P and P'. It can be shown that the result illustrated here holds for an arbitrary solid body. That is, the displacement of a rigid body is equivalent to the combination of its translation and a rotation about an axis. The translation from a given starting point P1 to the point P'1 during the time interval delta t is described by the vector pointing from P1 to P with the length delta s. If we consider rigid body motion during an infinitesimal interval of time, then the infinitesimal motion of the body consists of an infinitesimal translation given by the differential of the displacement and an infinitesimal rotation given by the differential of the rotation angle. For an infinitesimal translation, we can define the velocity of the translation by the ratio of the distance delta s of the translation to the time interval delta t, as delta t tends to 0. In other words, the magnitude of the translation velocity or the speed of the translation is equal to the derivative of the arc length s measured along the translation with respect to the time t. The rotation of the point P'1 about a given axis during the time interval delta t brings the point to the endpoint P2, where the rotation angle delta phi is measured between the sections OP'1 and OP2. For an infinitesimal rotation about an instantaneous axis of rotation, we can define the angular velocity omega of the rotation by the ratio of the angle delta phi of the rotation to the time interval delta t, as delta t tends to 0. That is, the angular velocity of the rotation is equal to the derivative of the rotation angle phi with respect to the time t. In the example shown as an illustration of the decomposition of the rigid motion, we saw that the translation of the rigid body, therefore the velocity of its translation depends on the choice of the starting point used for the translation, but the direction of the rotation axis and the angle of rotation do not. The angular velocity of the rotation is therefore independent of this choice. As a result, we can find a starting point for the translation such that the direction of the translation is the same as the one of the rotation axis. In other words, the displacement of the body can be described with a helical motion. This statement can also be illustrated with the same example, where the equiliteral triangle A1B1C1 is displaced into the position described by the triangle A2B2C2. We have a unique direction of the axis about which we can rotate the triangle while it is translated along the axis due to its independence of the position of the initial translation point. This choice results in a helical motion, where the points of the first triangle can be brought along helical trajectories into the corresponding points of the second one. In the case of the corners A1 and A2 of the two triangles, we can find a helix passing through the 2 points, where the axis of the helix is the axis of rotation. Then the trajectory of the moving point A1 during the interval of time delta t is the section of the helix connecting the points A1 and A2. Similarly, another helical path can be drawn with the same axis passing through the corners B1 and B2, and its section connecting the 2 points represents the trajectory of the moving point B1 during the same interval of time. A third helix passing through the corners C1 and C2 gives the path of the point C1 covered by its motion during the time interval delta t. If delta t tends to 0, we can talk about the motion during an infinitesimal interval of time, and we conclude that the most general motion of a rigid body can be interpreted as a series of infinitesimal helical motions. After having defined the angular velocity of a rotating rigid body, we show how to interpret this kinematic quantity as a vector. Let us consider a rigid body rotating about a fixed axis passing through the points O and A with the angular velocity omega. An arbitrary point P of the rotating body described by the position vector R has a circular trajectory around the point A, and we can apply the formula obtained for circular motion stating that the magnitude of the velocity v of the point P is given by its distance ρ from the axis, times the angular velocity omega. If the angle between the rotation axis and the position vector r is denoted by theta, then the distance ρ can be written as the length of the vector r times sine theta, and the speed of the point P is equal to omega times r, times sine theta. The right-hand side of this equation reminds us the magnitude of the cross product of two vectors given by the product of their magnitudes times the sine of the angle between them. As a result, we can consider the angular velocity omega as a vector lying on the rotation axis with its tail at the point O and with an orientation determined by the right-hand rule. By applying the notations of the figure, we can write this vector as omega times a unit vector pointing upward, where the unit vector is expressed as the vector pointing from the point O to the point A divided by its length. If we held the axis with our right hand and rotated the fingers in the direction of motion of the rotating body, then our thumb would point the direction of the angular velocity. In this figure the angular velocity omega points upward along the axis of rotation, whereas the instantaneous velocity v of the point P is the tangent to the circular path of the point, and perpendicular to the plane spanned by the angular velocity and the position vector r of the rotating point. Then the instantaneous velocity v of the point P of a rotating rigid body with the angular velocity omega is given by the cross product of the angular velocity vector omega and the instantaneous position vector r pointing from the point O to the point P. For infinitesimal rotations it is justified to consider the angular velocity as a vector, since the parallelogram rule holds for any two rotations with rotation axes intersecting each other at a given point. If the instantaneous angular velocity omega one of the body points in the direction of the OA axis, the infinitesimal displacement ds1 of the point P during an infinitesimal time interval dt is given by the product of the instantaneous velocity v1 of the point P and the time interval dt. Then the displacement is equal to the cross product of the angular velocity omega 1 and the position vector r of the point P, times dt. Similarly, for the angular velocity omega 2 pointing in the direction of the OB axis, the infinitesimal displacement ds2 of the point P is equal to the instantaneous velocity v2 times the time interval dt, that is the cross product of the angular velocity omega 2 and the position vector r, times dt. For both of the rotations, the infinitesimal displacements of the point P along its circular path are equal to the infinitesimal displacement vectors in the first order. If we rotate the point P with the angular velocities omega 1 and omega 2 either simultaneously or successively, then the net displacement ds of the point P is given by the vector sum of the displacements ds1 and ds2. However, we obtain the same net displacement if we compute the vector sum omega of the angular velocities omega 1 and omega 2, and construct the displacement ds as the cross product of the vector omega and the position vector r of the point P, times dt. This statement follows from the comparison of the similar triangles seen in the vector sums of the angular velocities and the displacement vectors. We can go even further in the interpretation of a rotation as a vector. Since the angular velocity omega of an infinitesimal rotation is a vector, its product with the infinitesimal interval of time dt is also a vector, and it can be interpreted as the infinitesimal rotation vector d phi. The infinitesimal change dr in the position vector r of a given point P of the rotating body is always perpendicular to both the axis of rotation, that is the vector d phi, and the instantaneous position vector r. As a result, the infinitesimal displacement of the point P can be written as the cross product of the infinitesimal rotation vector d phi and the position vector r. However, small but finite rotations cannot be considered as vectors because the parallelogram rule does not hold for them and the finite rotations are not commutative. For example, let us consider a cuboid in a Cartesian coordinate system. We can rotate the cuboid first about the x-axis by 90 degrees, and then about the y-axis by 90 degrees. But we can change the order of rotations and rotate it first about the y-axis by 90 degrees, and then about the x-axis by 90 degrees. As a result, the cuboid has different positions and orientations after the composition of rotations in the two cases. If any finite rotation can be constructed by the sum of the infinitesimal rotations, how can finite rotations be commutative and the infinitesimal ones not? In fact, infinitesimal rotations commute only in the first order, as we approximated the infinitesimal displacements along the circular path of the rotation with displacement vectors in the first order. If we study the general motion of a rigid body, we can choose the reference point O attached to the frame of reference and another reference point O' attached to the moving body given by the instantaneous translation vector R0. Then any point P of the body can be described by the position vector R pointing from the point O to the point P, and the relative position vector R minus R0 pointing from the point O' to the point P. We already saw that the instantaneous velocity v of an arbitrary point P of a rigid body performing a general motion can be combined from the translation and the rotation about the axis passing through the point O'. Here the translation velocity v0 of the body is given by the derivative of the translation vector R0 with respect to the time t. The origin O' was chosen such that the instantaneous axis of rotation with the angular velocity omega passes through it. Then the velocity v of the point P is given by its translation velocity v0, plus the cross product of the angular velocity omega of the rotation and the relative position vector R minus R0. Now we present the special cases of rigid body motion in terms of kinematics based on the degrees of freedom of the moving body. In the beginning of the study on the kinematics of rigid bodies, we introduced the degrees of freedom of their motion as the number of independent variables that determine the instantaneous position of a rigid body in space. Based on this concept, we can divide rigid motion into two general groups. The first group describes the free motion of rigid bodies, which is their most general motion since free motion has the maximum degrees of freedom. As already seen, the degrees of freedom f describing the free motion of a rigid body is equal to 6, where 3 data determines the coordinates of an arbitrary point of the body associated with the translational motion and called translational degrees of freedom, and 3 angles determine the orientation of the body known as rotational degrees of freedom. The second group describes the constrained motion of rigid bodies. In this case we talk about special motions where the degrees of freedom are less than the maximum, that is f is less than 6. For rigid motion we can write the degrees of freedom f as the difference between the maximum, that is 6, and the number n of the constraints imposed on the motion. We already studied constrained motion in the case of a point mass, and this concept can also be applied for a rigid body, where constraints are imposed either on its motion or its position, or on both, limiting its motion and position. For the rigid motion described in a coordinate system, constraints are given by the equations of geometric elements representing some restriction in the motion of the body. Such geometric elements can be some set of fixed points of the rigid body, curves, or surfaces. For example, a set of fixed points can determine one or more fixed points of a body or even a rotation axis passing through the body, along which the points of the body do not change their position during its rotation. Similarly, if a ball is attached to a string and whirled in a circle by hand, then the motion of the ball is constrained such that the curve describing its trajectory in space is a circle. In the third example, the ball rolls on a curved surface of a ramp preventing it from free fall, and the surface represents a constraint on the motion of the ball. These examples demonstrate that the points of the rigid bodies have no instantaneous displacements perpendicular to the curve or the surface representing the constraint. The ball whirled in a circle has no motion in the radial direction of its circular path, and the ball rolling on the curved surface had no instantaneous displacement in the direction of the surface normal. We can talk about several types of the constrained motion of rigid bodies depending on the number of constraints imposed on the motion. The first type of constrained motion is the motion of a rigid body on a surface, for example the motion of a wheel or a ball across a floor or a table. Here the degrees of freedom f of the moving body is equal to 5 since the translation perpendicular to the surface is forbidden during the motion. Such a motion has different cases. If we mark the instantaneous contact points of a moving ball across a table on both the ball and the surface of the table at given intervals of time, then the curve connected with the points P1, P2, P3 etc. on the surface, and the curve connected with the points P1', P2', P3' etc. on the ball can describe the motion of the center of the ball. If the arc lengths delta s measured between the corresponding adjacent points of the two curves are equal, that is the length of the section P1 P2 is equal to the length of the arc P1' P2', the length of the section P2 P3 is equal to the length of the arc P2' P3', and so on, then the ball rolls on the planar surface like a billiard ball moving across the table when it is hit with a cue stick. Otherwise we talk about rolling sliding motion instead of pure rolling, which can be also demonstrated with a billiard ball hit below its center. The ball performs pure sliding if the locations of the points P1, P2, P3 etc. on the ball remain the same as in the case of a bumper ball, which can also slide across ice. If the position of the contact point remains the same on both the rigid body and the surface, and the body rotates about an axis which is perpendicular to the surface and passes through the contact point, then the motion is called spinning or drilling. As an example, we can consider a marble spinning on a surface, or a more illustrative one of a basketball spinning on one finger. Another type of constrained motion is called spherical motion, where the rigid body is fixed at a point O such that it can rotate about this point, while any other point P of the body can move over a spherical surface with the center O. This type of motion can be considered as a series of infinitesimal rotations about instantaneous axes of rotation passing through the point O. As a result, the motion has only 3 rotational degrees of freedom given by either the Euler angles, or more generally by 2 angles describing the direction of the instantaneous rotation axis and a third angle measuring the rotation of the body about this axis. A typical example of spherical motion is the swinging of a spherical pendulum, where the deepest points of the tracks drawn in the sand by the tip of moving bob have a constant distance from the suspension point O of the pendulum, that is, they are running over a sphere with the center O. Another well-known example is the spinning top with its tip constrained to a cup. While its tip remains at the bottom of the cup, the top spinning rapidly about its own axis can also precess around a vertical axis through its point of support. The third type of the constrained motion of a rigid body is its planar motion, where the trajectories of the points of the body are parallel with a fixed plane in the space. For example, in the case of a box sliding across the xy plane over an arbitrary path, the position of the body is determined by the positions of 2 points A and B of the body lying in the xy plane. As a result, the degrees of freedom of the moving box is equal to 3, and this data can be, for example, the x and y coordinates of either the point A or the point B, and the angle phi between the segment AB and the x-axis. This happens when we slide or rotate furniture on the floor. The planar translation of an object, for example a motion of a wheel across the floor in a given direction, is a special case of planar motion since the degrees of freedom f is reduced to 2. The condition of rolling for a wheel can be illustrated in the figure of the rolling ball, and it states that the delta s arc length of its trajectory must be equal to the radius r of the wheel, times the angle delta phi measuring the rotation about its axis. Here the instantaneous axis of rotation is perpendicular to the plane of the wheel, and the axis of the wheel is translated in the direction parallel with the plane of the wheel. The last type of constrained motion is where the degrees of freedom of the moving rigid body is equal to 1. We can talk about 2 cases of this type of motion. The first case is the linear translation of a body, where one coordinate can measure the displacement of the body along the translation vector. Here the trajectory connecting the initial and final positions of an arbitrary point A of the body is a straight segment across the xy plane, and the distance between the 2 positions is the single degree of freedom determining the motion. A typical example for linear translation of the motion of the printer head during printing. The second case is when 2 points of a rigid body are fixed and the body can only rotate about the fixed axis passing through the 2 points. A well-known example for such motion is the operation of ball bearings, where one of the races is fixed while the other one is allowed to rotate by the separated balls between the races. Here the only degree of freedom of the motion is the rotation angle of the moving race. Helical motion has also only 1 degree of freedom, as the example of a nut turning on a bolt shows. Although this motion is the composition of a translation and rotation, the rotation angle uniquely determines the position of the nut along the axis of the bolt. Vice versa, the displacement of the nut along the axis of the bolt also determines the rotation angle of the turning nut. In the discussion on rigid body kinematics, we demonstrated that the motion of a rigid body can be interpreted as a composition of translations and rotations. Now we examine how to describe these 2 types of special motions in coordinate representation. As already seen, we talk about translation if all the points of a rigid body simultaneously move along congruous curves parallel with each other. These curves are arbitrary curves in space, but in the case of linear translation they consist of straight line segments. Linear translation is an important special case since it is often used to study the relations between different frames of references. The distance and the direction of a translation are determined by the length and the direction of the translation vector. If an arbitrary point P of a rigid body is described by the position vector r with respect to some reference point O, then the position vector r' of the point P after the translation of the body is given by the vector sum of the position vector r and the translation vector delta r. In order to give the coordinate representation of translation, we can attach the origin of a Cartesian coordinate system to the reference point O and describe the position vectors r and r' with its x, y, and z components. Similarly, the Cartesian components of the translation vector can be written as delta x, delta y and delta z. These coordinates represent the three translation degrees of freedom of rigid bodies translated in space, and we can consider translation as a point transformation of three parameters. Then the vector equation of translation represented in Cartesian coordinates states that the components x', y', and z' describing the position of the point P after translation are equal to the coordinates x, y, and z of the vector are describing its original position, plus the coordinates delta x, delta y, and delta z of the translation vector. The components of the position vector r' are simply the sums of the components of the position vector r and the translation vector delta r. By choosing the orientation of the coordinate system such that one of the coordinate axes points in the direction of the linear translation of the body, we can simplify the coordinate representation of the translation. For example, if the z-axis points in the direction of the translation vector delta r, then the only non-zero component of delta r is its z-coordinate delta z. As a result, the first two Cartesian components of the position vector of point P after translation do not change, and its z-component is given by z plus delta z. Obviously, it does not mean that we reduce the degrees of freedom of linear translation to 1, since the special choice of the orientation of the coordinate axes with the reduced number of parameter or parameters gives the complete data for the 3 degrees of freedom of the point transformation. However, this simplification still makes Cartesian coordinates very useful in the quantitative description of linear translations. Curvilinear coordinate systems are less convenient to be adapted to the linear translation of rigid bodies. We can still use a cylindrical coordinate system to simplify the representation of translation by directing its z-axis parallel with the translation vector, and reduce the non-zero parameters of the translation to the z-coordinate. There is no such option for spherical polar coordinates. Even if we translate a rigid body in radial direction, the polar and azimuthal angles of any point of the body still change after the translation. Now we derive the coordinate representation for the rotation of rigid bodies. Starting with the planar rotation of the points of a rigid body, we determine the coordinate representation of the rotation of a point in a Cartesian coordinate plane. Let us attach a Cartesian coordinate system to a frame of reference such that the origin of the coordinate system is at the reference point O of the frame, and a given point P of a rigid body is on the positive x-axis. That is, the position vector r of the point P points in the direction of the positive x-axis. If we rotate the point P about the origin through the angle alpha in the xy plane, then we obtain the point P' described by the position vector r'. The Cartesian coordinates of the point P are given by x and y, whereas the coordinates of the point P' are denoted by x' and y'. Since we rotated the position vector r about the origin O, its length is equal to the length of the position vector r'. As a result, we can write the x-coordinate of the point P' as the magnitude r times cosine alpha, which is equal to x times cosine alpha. Similarly, the y-coordinate of the point P' is given by the magnitude r times sine alpha, or x times sine alpha. Now we can consider a more general case, where the point P is not on the x-axis and the angle alpha measured between its position vector r and the positive x-axis is arbitrary. Here the coordinates x and y of the point P are given by the length of the position vector r times cosine alpha, and r times sine alpha respectively. Now we rotate the point P about the origin O through the angle beta in the xy plane, and obtain the point P' with the coordinates x' and y' given by r times the cosine of the sum of the angles alpha and beta, and r times the sine of the sum of alpha and beta respectively. By applying trigonometric relations for the cosine and the sine of the sum of the angles, we can write the coordinates of the point P' as follows. The coordinate x' can be written as r times the difference between cosine alpha times cosine beta and sine alpha times sine beta. If we expand the brackets in the right-hand side of the equation, then we obtain r times cosine alpha times cosine beta, minus r times sine alpha times sine beta. By substituting the coordinates x and y of the point P into the products, we can write the coordinate x' as x times cosine beta minus y times sine beta. Similarly, the coordinate y' can be written as r times the sum of sine alpha times cosine beta and cosine alpha times sine beta. The right-hand side is equal to r times sine alpha times cosine beta, plus r times cosine alpha times sine beta, which gives y times cosine beta plus x times sine beta. As a result, the coordinates x' and y' of the point P' rotated about the origin through the angle beta in the xy plane are given by the following equations. X' is equal to the x-coordinate of the point in its initial position times the cosine of the rotation angle beta, minus the y-coordinate of the point in its initial position times sine beta. y' is given by the y-coordinate times the cosine of the angle beta, plus the x-coordinate times the sine of the angle beta. We can also write these two equations in vector notation, where the column vector in the left-hand side describes the coordinates of the point P', and the right-hand side is the product of a 2 times 2 matrix and the column vector describing the coordinates of the point P. Here the matrix with the elements cosine beta, minus sine beta and cosine beta is the coordinate representation of the rotation of a point about the origin O through the angle beta in the xy plane, which is also called the rotation matrix of the planar rotation. We can generalize planar rotations about the origin of a Cartesian coordinate system to spatial rotations about one of the coordinate axes, and determine their coordinate representation by using the one derived for planar rotations. The straightforward generalization of the rotation of a point in the xy plane is the rotation of the point P about the z-axis in a plane parallel with the xy plane. The distance of the plane of rotation from the xy plane is given by the coordinate z at the point O, where the z-axis passes through the plane of rotation. The coordinates of the position vector are pointing from the point O to the point P are the coordinates x, y and z, where the coordinates of the position vector are prime pointing from the point O to the point P' are described by the primed Cartesian coordinates. Here the angle alpha is measured between the xz plane and the position vector r, and beta is the angle of rotation measured between the position vectors r and r'. In the case of planar rotation, we obtain the x' and y' coordinates of the point P by multiplying the column vector of the x and y coordinates of the point P with the rotation matrix. We can extend this two-dimensional equation to a three-dimensional one if we take into account the fact that the z-coordinate of the point P is invariant under the rotation, that is z' is equal to z. As a result, we can write the coordinates of the point P' given by the column vector of the coordinates x', y' and z' as the product of a 3 times 3 matrix and the column vector of the coordinates x, y and z. The matrix of the planar rotation in the xy plane forms the first two rows and columns of the matrix of the spatial rotation, whereas the third row and the third column of the matrix are constructed from zeros and the number 1 such that the multiplication of the in the right-hand side gives the primed coordinates where z' is equal to z. Then the 3 times 3 matrix in the right-hand side of the vector equation is called the rotation matrix of the rotation of any point about the z-axis through the angle beta. We will follow the same procedure to derive the rotation matrices for the rotations about the x and y axes of the Cartesian coordinate system. For the rotations about the x-axis we can choose any plane of rotation parallel with the yz plane. Here the plane of rotation passes through the x-axis at the point O, and the position vectors r and r' pointing from the point O to the points P and P' are parallel with the yz plane. The coordinates x', y' and z' of the point P' are expressed as the product of a 3 times 3 matrix and the column vector of the coordinates x, y and z. Now the matrix of the planar rotation in the yz plane forms the second and the third rows and columns of the matrix, where the first row and column are constructed such that the multiplication of the matrix and the column vector in the left-hand side gives the primed coordinates where x' is equal to x. 10. This matrix is the rotation matrix of the rotation of a point about the x-axis through the angle beta. Similarly, we can determine the coordinate representation of the rotations about the y-axis by choosing any plane of rotation parallel with the zx plane. In this case the plane of rotation passes through the y-axis at the point O, and the position vectors r and r' pointing from the point O to the points P and P' are parallel with the zx plane. The column vector of the coordinates of point P' are given by the product of a 3 times 3 matrix and the column vector of the coordinates of the point P. Here the second row and column of the matrix vanish except the diagonal element, which is 1. The rest of the elements in the corners of the matrix are constructed from the matrix of the planar rotation in the zx plane through the angle beta. Since the direction of the rotation is the opposite to the one for the first two cases, the rotation angle beta has a negative sign which changes the sign of sine beta since it is an odd function. The resulting 3 times 3 matrix is the rotation matrix of the rotation about the y-axis through the angle beta. Then we have 3 matrices providing the coordinate representation of spatial rotations about the 3 Cartesian coordinate axes. The matrix R x hat alpha represents the rotation of an arbitrary point about the x-axis through the angle alpha, where the bold-faced letter x with hat denotes the unit vector pointing from the origin in the direction of the x-axis. Similarly, the matrices R y hat alpha and R z hat alpha represent the rotations about the y and z axis respectively, where y hat and z hat are the unit vectors pointing in the direction of the y and z axes and alpha is the angle of the rotations. In the general case, rigid bodies can be rotated about an arbitrary axis in the space, and the properties of the rotation matrices for general rotations can also be determined without selecting any specific direction for the rotation axis. The figure shows a rigid body rotating about the axis specified by the unit vector n through the angle alpha. The orientation of the vector n is chosen such that it forms a right-handed system with the positive direction of the rotation. As a result, the point P described by the position vector are pointing from a reference point O on the rotation axis to the point P is rotated to the point P' described by the position vector R' pointing from the point O to the point P'. Then the position vector R' can be written as the product of the rotation matrix Rn alpha representing the rotation and the position vector R. Here the 3 times 3 matrix R is the rotation matrix for rotations about the unit vector n through the angle alpha, where the elements of the matrix depend on the direction of the vector n and the rotation angle alpha. Although the axis and the angle of rotation are arbitrary, rotation matrices have some general properties which we present here. The first property immediately follows from the fact that the distance between any 2 points of a rigid body is constant during its motion. This distance is therefore invariant under the rotation of the body, and the length of the position vector R with the tail on the axis does not change when the body is rotating about the axis. As a result, the magnitude of the position vector R' of the point after the rotation is equal to the magnitude of the initial position vector R. In other words, the scalar product of the vector R' with itself is equal to the scalar product of the vector R with itself. Here the position vector R' can be written as the product of the rotation matrix Rn alpha and the position vector R. Since the scalar product of 2 vectors in coordinate representation is actually the product of a column vector and a row vector, the column vector of the left-hand side factor in the dot product can be written as the transpose of the product of the matrix R and the position vector R. The transpose of the product is equal to the vector R times the transpose of the matrix R. If we compare the 2 sides of the vector equation, then we conclude that the transpose of the matrix R times the matrix R must be equal to the unit matrix I. 2 important results follow from this equation. The first one tells us that the transpose of the rotation matrix R is equal to its inverse. The second result is based on the fact that the determinants of a matrix and its transpose are equal, and tells us that the square of the determinant of the matrix R is equal to 1. Such matrices are called orthogonal matrices, that is, the rotation matrix of a general rotation is an orthogonal matrix. Other properties of the rotation matrix also follow from geometric considerations. We can rotate a rigid body about a fixed axis of rotation given by the unit vector n in 2 steps. First we rotate the body through the angle α1, and then through the angle α2, which is equivalent to the rotation of the body in 1 step through a rotation angle given by the sum of the angles α1 and α2. The matrix representation of this property is expressed by the equation stating that the product of the rotation matrices Rn α1 and Rn α2 is equal to the rotation matrix Rn α1 plus α2. Although the matrix multiplication is not commutative, the order of the factors in the product does not matter for rotations about the same axis. Another important property is the periodicity of the rotation angle. It is obvious that a rigid body does not change its orientation if we rotate it through 360 degrees, that is, we have an identity transformation. In the general case, we describe the periodicity of rotations by stating that the rotation matrix Rn alpha plus 2 pi times k is equal to the rotation matrix Rn alpha, where k is an arbitrary integer number. It is also clear that the inverse rotation of a rigid body about a given axis through a given angle is equivalent to its counterclockwise rotation about the same axis through the same angle. In a mathematical representation, the inverse of the rotation matrix Rn alpha is equal to the rotation matrix Rn minus alpha. Due to the convention used for the orientation of the unit vector n, we can write the right-hand side as the rotation matrix R minus n alpha. It follows from the periodicity of rotations and the properties of inverse rotations that the rotation matrix R of the rotation about the axis given by the unit vector n through the angle 2 pi minus alpha is equal to the rotation matrix Rn minus alpha. The right-hand side is equal to the rotation matrix R minus n alpha, that is, any spatial rotation of a rigid body can also be described by a counterclockwise rotation through the original rotation angle alpha plus 180 degrees. We already saw that the spatial rotation of rigid bodies can be described by the Euler angles. The axis and the angle of rotation determines the rotation matrix, and the Euler angles of the rotations can be computed from the elements of this matrix. Conversely, General rotations can be constructed from Euler rotations, that is, the rotation matrices of general rotations can be expressed in the terms of the Euler angles. When we define the Euler angles by introducing the three Euler rotations of a Cartesian coordinate system, we use the following convention. First, we rotate the coordinate system counterclockwise about its z-axis through the angle psi. Then we rotate the coordinate system counterclockwise about its x-axis through the angle theta. In the last step, we rotate the coordinate system counterclockwise about its z-prime axis through the angle phi such that the axes x and y are brought into the x-prime and y-prime axes. If we attach a rigid body to the coordinate system and rotate them together and describe the position of the points of the body in the original coordinate system, then the product of the rotation matrix and the position vector of any point of the body gives the new position of the point after rotation. Since the Euler rotation is the composition of the three rotations of the Cartesian coordinate axes, the rotation matrix R expressed in the terms of the Euler angles psi, theta, and phi can be written as the product of the rotation matrices R z hat prime phi, R x hat theta, and R z hat psi. In order to compute the product of the three matrices, we start with the multiplication of the second and the third matrices in the product. We write the elements of the third matrix, that is the matrix R z hat psi, in a table, and the elements of the second matrix, that is the matrix R x hat, in another table such that their mutual positions determine the result of their multiplication. This arrangement facilitates the computation of any element in a given row and a given column of the product matrix obtained from the dot product of the corresponding row of the second matrix and the corresponding column of the third matrix. The product of the first row of the second matrix and the first column of the third matrix and gives the top left element of the resulting matrix, which is equal to cosine psi. The product of the first row of the second matrix and the second column of the third matrix is equal to minus sine psi for the top middle element of the resulting matrix. The product of the first row of the second matrix and the third column of the third matrix gives the vanishing top right element of the resulting matrix. Similarly, the product of the second row of the second matrix and the first column of the third matrix gives the middle left element of the resulting matrix, which is equal to cosine theta times sine psi. The product of the second row of the second matrix and the second column of the third matrix is equal to cosine theta times cosine psi for the element in the center of the resulting matrix. The product of the second row of the second matrix and the third column of the third matrix gives minus sine theta, the middle right element of the resulting matrix. The product of the last row of the second matrix and the first column of the third matrix gives the bottom left element of the resulting matrix, which is equal to sine theta times sine psi. The product of the last row of the second matrix and the second column of the third matrix is equal to sine theta times cosine psi for the bottom middle element of the resulting matrix. The product of the last row of the second matrix and the last column of the third matrix gives cosine theta, which is the bottom right element of the resulting matrix. If we multiply this result with the first matrix in the product, that is with the matrix R z hat prime phi, then we obtain the general rotation matrix in the terms of the Euler angles. The product of the first row of the first matrix and the first column of the resultant matrix gives the top left element of the general rotation matrix. The first row of the first matrix multiplied by the second column of the resultant matrix gives the top middle element of the rotation matrix. The product of the first row of the first matrix and the last column of the resultant matrix is equal to the top right element of the rotation matrix. Similarly, the product of the second row of the first matrix and the first column of the resultant matrix gives the middle left element of the general rotation matrix. The second row of the first matrix multiplied by the second column of the resultant matrix gives the central element of the rotation matrix. The product of the second row of the first matrix and the last column of the resultant matrix is equal to the middle right element of the rotation matrix. The product of the last row of the first matrix and the first column of the resultant matrix gives the bottom left element of the general rotation matrix. The last row of the first matrix multiplied by the second column of the resultant matrix gives the bottom middle element of the rotation matrix. Finally, the product of the last row of the first matrix and the last column of the resultant matrix is equal to the bottom right element of the rotation matrix. As a result, we have obtained the rotation matrix of general rotations in terms of the Euler angles psi, theta and phi. Although this matrix seems to be somewhat complicated, its inverse, that is the matrix of the inverse Euler rotations, is simply given by the transpose of this matrix. The rotation matrix can also be used to determine the Euler angles for the general rotation if its rotation matrix is already given. For a rotation axis described by the unit vector n and the rotation angle alpha, we can compute the elements R sub ij of the rotation matrix Rn alpha as the functions of the Cartesian components of the unit vector and the angle alpha, where the indices I and j run from 1 to 3. Since this general form of the rotation matrix is equal to the rotation matrix expressed in terms of the Euler angles, the individual elements of the two matrices are the same. Then we can express the Euler angles as the functions of the elements R sub ij. For example, by comparing the elements in the bottom right corners of the matrices, we can express the Euler angle theta as the arc cosine of the element R sub 3. We use the index 1 for the angle since it is determined up to a shift of 180 degrees, that is pi plus theta 1 is also a solution and theta 2 can be written as pi plus the arc cosine of the element R sub 3. If theta 1 and theta 2 are given, we can determine the other two Euler angles as well. After dividing the elements R sub 3 and R sub 3 by sine theta 1, we take their ratio and express the angle psi 1 as the arctangent of the ratio of R sub 3 divided by sine theta 1 to R sub 3 divided by sine theta 1. We have the same expression for psi 2, where the matrix elements are divided by sine theta 2. Similarly, we can divide the elements R sub 1 and R sub 2 by sine theta 1, and express the angle phi 1 as minus the arctangent of the ratio of R sub 1 divided by sine theta 1 to R sub 2 divided by sine theta 1. We have the same expression for phi 2, where the matrix elements are divided by sine theta 2. As a result, we have two representations of the general rotation matrix expressed either in the terms of the unit vector n determining the rotation axis and the rotation angle alpha, or in the terms of the Euler angles psi, theta and phi. We note that there are several conventions for the definition of the Euler angles with different notations for the angles and different sequences of the Euler rotations for the coordinate axes. If we apply a different convention, then the rotation matrix seen in the top will have a different form and the expressions obtained for the Euler angles will be different as well. However, the procedure for their derivation presented here is still the same. As already seen above, we can simplify the description of the translation of rigid bodies in space by using a Cartesian coordinate system with one of its axes pointing in the direction of the translation. In the case of the rotating rigid bodies, we can also adapt coordinate systems to the trajectories of the motion, and use curvilinear coordinates in the description of the points of rotating bodies. We can study the motion of a rotating rigid body in a cylindrical coordinate system if the body rotates about a fixed axis. Any two fixed points of a rigid body determine an axis about which the body can rotate, for example a bicycle will attach to its axle. In other cases rigid bodies can rotate over some constrained surface like a toy train moving on a circular track, or a ball bearing where one of the races is fixed while the other one is allowed to rotate by the separated balls between the races. The description of such a motion becomes very simple in a cylindrical coordinate system with its origin on the axis while its z-axis points in the direction of rotation axis of the body. Any point P of the rotating body can be described by the position vector r with the coordinates ρ, phi and z. Since the coordinate ρ is the distance of the point from the axis of the coordinate system that is the axis of rotation, it is invariant under the rotation of the body. Similarly, the points of the body do not move along the axis z, and the z-coordinate of their rotating position vector remains constant. If r' denotes the position vector of the point P' after rotation, we can write the vector equation stating that the components ρ', phi' and z' of the vector r' are equal to ρ, phi plus delta phi and z respectively. Here delta phi gives the change in the azimuthal angle of the rotating point. As a result, the azimuthal angle completely describes the motion of the rigid body during its rotation, which simplifies the analysis of the problem. A spherical coordinate system can be used to describe rotating motion as well. If we fix only one point of the rigid body, then it can rotate about the fixed point in an arbitrary direction. As a result, all the points of the body can be rotated over the spheres of radii given by the distances of the points from the fixed point, that is from the center of rotation. Typical examples of such a spherical rotation are a spinning top with its tip constrained to a cup with its top end slowly revolving about the tip, and a spherical pendulum swinging on a surface of a sphere. By using a spherical coordinate system with its origin at the center of rotation, we can simplify the description of the motion of the rotating body. The position vector of any point P of the body has the components describing its distance are from the center, the polar angle theta and the azimuthal angle phi. If r' denotes the position vector of the point after rotation, then we can write the vector equation stating that its primed coordinates are equal to r, theta plus delta theta, and phi plus delta phi respectively. Since the polar and azimuthal angles of the rotating points describe the motion of the rigid body, we only need to study the change in these two coordinates during the rotation. In both cases, the trajectories of the points of the rigid body have a simple description in curvilinear coordinates and no rotation matrix is needed to transform the coordinates of an initial point to the ones of the point after rotation. Although curvilinear coordinate systems adapted to the symmetries of rotation simplify the study of the motion of the rigid bodies, their application are only convenient if the center or the axis of rotation is fixed. Otherwise, it is better to use Cartesian coordinates to describe the motion of a rigid body rotating about an instantaneous center or axis. The application of a Cartesian coordinate system attached to the frame of reference is the most general method for the quantitative description of the rotating motion of rigid bodies without fixed center or axis of rotation, where kinematics is described by the action of rotation matrices on the points of the rotating body. In the context of the coordinate representation of rotations, we need to mention another type of point transformation, and this is reflection. At first sight, reflections of geometric points in space do not seem to have anything to do with the physical motion of rigid bodies, but this geometric transformation has an important role in the classification of rotations. When we talk about the reflection of a rigid body in space, we imagine an arbitrary plane in the vicinity of the body serving as a plane of reflection. The image of the body appears on the opposite side of the plane, and it has the same distance from the plane of reflection as the rigid body. If the images of the points A, B, C and D of the body are denoted by the primed letters, then we can write that the distance d sub AO is equal to the distance d sub A prime O. That is the intersection point O of the section AA prime, and the plane of reflection is the midpoint of the section AA prime. Similar equations can also be given for the points B, C, D and for other arbitrary points of the rigid body with the corresponding points of intersection. We can also see that although the shape of the image remains congruent to the original, it has a reverse orientation. That is, the image does not flip left to right. If the original points A and B are in the front, then the reflected points A' and B' are in the front as well. We can obtain the coordinate representation of the reflection if we attach a Cartesian coordinate system to the plane of reflection such that one of its coordinate plane, for example the YZ plane, is in the plane of reflection. If any point of the rigid body has the x, y and z coordinates in this coordinate system and its image has the primed Cartesian coordinates, then the distance equation of the original points and their images has the coordinate representation stating that the coordinates x', y' and z' of the image are equal to -x, y and z, respectively. The right-hand side can be written as the product of a 3x3 diagonal matrix and the column vector x, y and z, where the non-zero component in the diagonal are -1, 1 and 1. This matrix is the coordinate representation of the reflection across the YZ coordinate plane, and it is denoted by p sub x hat, where the unit vector x hat is the normal to the plane of reflection. We can derive the reflection matrices for the other two coordinate planes as well, where all the Cartesian reflection matrices p sub x hat, p sub y hat and p sub z hat are diagonal matrices, with the diagonals 1, -1, 1 for p sub y hat, and 1, 1, -1 for p sub z hat. If the normal to the plane of reflection has an arbitrary direction, we can rotate the plane together with the body into any of the coordinate plane, perform the reflection of the body and apply an inverse rotation on the image. We have already shown that rotations can be represented by orthogonal matrices, which are denoted by the capital letter O. In other words, the square of the determinant of a general rotation matrix is equal to 1. As a result, the determinant is equal to either +1 or -1. If the determinant of a matrix is equal to 1, we call it as a special orthogonal matrix denoted by the capital letters SO, and such matrices represent the proper rotations of rigid bodies in space. If the determinant of a matrix is equal to -1, then it can be written as the product of a special orthogonal matrix and a reflection matrix. In other words, it is a composition of a proper rotation and a reflection in space. Such operations are also known as improper rotations. Then we conclude that a general rotation about an axis given by the unit vector n through the angle alpha is represented by special orthogonal matrices, which can have different elements in different coordinate systems but their determinant is always equal to 1. Improper rotations are represented by the product of a special orthogonal matrix are depending on a given unit vector n and angle alpha and a reflection matrix Pm, where m is the unit normal to a plane of reflection. Although we do not discuss the cause of the change in the state of motion of bodies in kinematics, here we make an exception. In order to give a more detailed description on rigid rotation, we need to consider how forces are applied on rigid bodies. First, we demonstrate the theorem of transmissibility of forces by presenting a simple example, since the theorem has a fundamental role in the study of forces acting on rigid bodies. In the case of point masses, the effect changing of their state of motion is completely described by a force F acting on the point mass m, where the force vector has a given magnitude and direction. In the case of a rigid body, this information is not unique due to the size and extension of the body. In order to give a complete description of the effect changing its state of motion, we need to specify both the point P of the application of the force F, that is the point of the body where the force is applied, and the line of action of the force, that is the line along which the force acts. A system of forces simultaneously acting on a point mass can be replaced with the vector sum of the system. If the net force given by the vector sum is zero, that is the forces acting on the point mass are balanced, then they do not have an effect on the state of motion of the point mass. In the case of rigid bodies which are not point-like objects, the superposition and the balance of forces are more complicated problems, since the points of application of the individual forces are generally different. For example, let us place a board on 3 balls of the same size such that the balls rolling on the floor allow the board to move horizontally. If a pair of forces F and minus F, that is 2 forces of the same magnitude but opposite in direction, are applied on the board at the points P1 and P2, then the board either rotates about some vertical axis even if the net force acting on it vanishes, or stays at rest. The result is due to the fact that the lines of action of the forces are different in the first case and are coincident in the second one. The findings in this example can be formulated as follows. A rigid body under the influence of a pair of forces with the same magnitude but opposite in direction is in equilibrium if the lines of action of the forces are coincident. Then the pair of forces has no net effect on the body. Let us suppose that the force F is applied on the body at the point P1. We can also apply the pair of forces F and minus F at any point P2 on the line of action of the force F exerted at the point P1. Based on our statement, the force F applied at the point P1 and the force minus F applied at the point P2 do not have any net effect of the body, and they can be neglected. As a result, the force F acting at the point P1 can be replaced with the force F acting at the point P2. This result is expressed in the theorem of transmissibility of forces, stating that the point of application of a force acting on a rigid body can be moved anywhere along its line of action without changing its external effect on the body. The force acting on a rigid body can be translated along its line of action like the vector of angular velocity, which can be translated along the axis of rotation. In other words, the external effects of the force on a rigid body is independent of the point of application of the force along its line of action. The fact that the line of action is more important than the point of application has a crucial role when we determine how a system of forces acting on a rigid body can be replaced with an equivalent but simpler system of forces with the same external effect. This is the problem of the reduction of a system of forces, and we start the discussion of this topic with the analysis of some simple examples. First, we consider the superposition of non-parallel planar forces, that is, forces with intersecting lines of action lying in one plane. Let us suppose that P1 and P2 are the points of application of the forces F1 and F2 acting on a rigid body. We translate the forces F1 and F2 to the point of intersection A of their lines of action, and determine their net force F by using the parallelogram law. Obviously, the point of application of the force F is arbitrary along its line of action. This result can be demonstrated by attaching 3 dynamometers to the points of application P1 and P2 in the intersection point A. The rigid body under the influence of the forces F1, F2 and F applied by the dynamometers at the points P1, P2 and A is in equilibrium, indicating the balance between these forces. If a third force F3 is also applied at the point P3 of the rigid body, we compute the net force F of the forces F1 and F2 and replace them with the force F. Then we can determine the superposition of the forces F3 and F in the same way as we did it for the forces F1 and F2. That is, we translate the forces F3 and F to the point of intersection B of their lines of action, and construct their net force F' by using the parallelogram law. We can repeat the same procedure for the force reduction if we add another force to the system of forces acting on the rigid body. We note that the 2 right-angled triangles with the sides D1' and D2' at the tail of the force F are similar because their angles alpha are angles in parallel lines. Since the lengths of the sides of the triangles formed by the parallelogram are equal to the lengths of the forces F1 and F2, we can write that the ratio of the length D1' to the length D2' is equal to the magnitude of the force F1 over the magnitude of the force F2. Furthermore, if the distances of the lines of actions for the forces F1 and F2 from an arbitrary point P on the line of action for the force F are denoted by D1 and D2, then the ratio of D1' to D2' can be written as the ratio of D1 to D2. By combining these 2 equations, we obtain the following relationship for any point P on the line of action of the net force F of the forces F1 and F2. The product of the magnitude of the force F1 and the distance d1 between the point P and the line of action of the force F1 is equal to the product of the magnitude of the force F2 and the distance d2 between the point P and the line of action for the force F2. We will use this relation in the analysis of rigid rotation. In the next example, we determine the superposition of parallel planar forces, that is, two forces pointing in the same direction. Let us suppose that P1 and P2 are the points of application of the forces F1 and F2 acting on a rigid body. Due to the theorem of transmissibility, these points can be chosen such that the section P1-P2 is perpendicular to the line of actions of the forces F1 and F2. Although the lines of actions have no point of intersection, this problem leads back to the previous case if we apply the auxiliary forces F' and -F' at the points P1 and P2 with the lines of action coincident with the section P1-P2. So that these forces cancel each other out. By using the parallelogram law, we can determine the net force F1' of the forces F1 and F'. Similarly, the vector sum of the forces F2 and -F' gives the force F2'. Now we translate the forces F1' and F2' to the point of intersection A of their lines of action, and determine their net force F by using the parallelogram law. Since the force F1' is equal to the vector sum of the forces F1 and F', and F2' is equal to the vector sum of F2 and -F', the auxiliary forces F and -F' cancel each other out in the vector sum of F1' and F2'. As a result, the magnitude of the net force F is given by the sum of the magnitudes of the forces F1 and F2. The point of intersection O of the line of action of the net force F and the section P1-P2 is the center of the parallel forces F1 and F2. This center is always nearer to the point of application of the force that is the bigger one in the pair. If d1 denotes the distance between the points P1 and O, and d2 is the distance between the points P2 and O, then we can write that the ratio of the length of the section AO to the distance d1 is equal to the magnitude of the force F1 over the magnitude of the force F' due to the similarity of the triangles OAP1 and B1C1P1. Similarly, the ratio of the length of the section AO to the distance d2 is equal to the magnitude of the force F2 over the magnitude of the force F', because the triangles OAP2 and B2C2P2 are similar. We can therefore write that the length of the section BO times the magnitude of the force F' is given by the magnitude of the force F1 times the distance d1, which is equal to the magnitude of the force F2 times the distance d2. In another form, this equation states that the distance d1 divided by the distance d2 is equal to the magnitude of the force F2 divided by the magnitude of the force F1. We can generalize this result by translating one of the points of application of the forces F1 and F2, and conclude that the parallel forces F1 and F2 of the same orientation applied at the points P1 and P2 of a rigid body can be replaced by a net force F, which is parallel with the given forces and its magnitude is equal to the sum of the magnitudes of these forces. The line of action of the force F is determined by the position of the point O, where the length L1 of the section P10 divided by the length L2 of the section P20 is equal to the distance d1 over the distance d2. These two ratios are equal to the magnitude of the force F2 over the magnitude of the force F1, which can be written as the equation stating that F1 times d1 is equal to F2 times d2. This theorem can be demonstrated by using the apparatus shown in the figure where a light rod is suspended from two ropes through pulleys with some weights suspended from the other ends of the ropes. As a result, the forces F1 and F2 pointing upward are exerted on the rod at the points P1 and P2 through the ropes. The whole system is in balance if we suspend a weight G from the rod at the point O, where the magnitude of the weight G is given by the sum of the magnitudes of the forces F1 and F2. The forces F1 and F2 can therefore be replaced by the force F applied at the point O. Let us suppose that the forces F1, F2 and G are exerted on the rod by suspending 3, 2 and 5 units of weight respectively, and the distances d1 and d2 of the point O from the points P1 and P2 are 4 and 6 units of length respectively, as seen in the figure. It can be demonstrated that the system with such a setup remains at rest, that is the equation stating that G is equal to F1 plus F2 holds. Numerically, 5 units of weight is equal to 3 units of weight plus 2 units of weight. Similarly, the equation stating that F1 times d1 is equal to F2 times d2 holds as well, as its numerical form shows that 3 units of weight times 4 units of length is equal to 2 units of weight times 6 units of length. Now we discuss an example where we determine the superposition of antiparallel forces acting on a rigid body. First we consider forces of different magnitudes. Let us suppose again that P1 and P2 are the points of application of the forces F1 and F2 acting on a rigid body, where the magnitude of the force F2 is greater than the magnitude of the force F1. Here we can still follow the same procedure as described in the previous example. We apply the pair of the auxiliary forces F' and minus F' at the points P1 and P2 and determine the net forces F1' and F2' acting at the points P1 and P2. Then we translate these forces to the point of intersection A of their lines of action, and determine the net force F by using the parallelogram law. As in the previous example, we can translate the force F along its line of action and conclude that the magnitude of the net force F of the forces F1 and F2 is given by the difference between their magnitudes, and its line of action is determined by the equation stating that the magnitude of the force F1 times the horizontal distance d1 between the point P1 and the point O, is equal to the magnitude of the force F2 times the horizontal distance d2 between the point P2 and the point O. The force F replacing the antiparallel forces F1 and F2 points in the same direction as the force F1 since the force F1 has greater magnitude than the force F2, and the point P2 is located between the points P1 and O. In order to demonstrate this result, we can apply the same apparatus as used in the previous problem. The rope in the right-hand side exerts the force F1 upon the rod at the point P1, which is still one of the antiparallel forces, whereas the weight G acting on the point O represents the other one of the antiparallel forces. The net force of the antiparallel forces is a force that has the magnitude F1 minus the magnitude of G, and it is applied at the point P2 and points downward cancelling the force F2. The equation stating that the magnitude of F2 is equal to the magnitude of G minus the magnitude of F1 has the following numerical form. 2 units of weight is equal to 5 units of weight minus 3 units of weight. For the equation stating that F1 times D1 is equal to F2 times D2, we can write that 3 units of weight times 10 units of length is equal to 5 units of weight times 6 units of length. Now we consider antiparallel forces of the same magnitude. If the lines of action of the forces are not coincident, then we cannot use the procedure presented here because the lines of action constructed by applying the auxiliary forces have no intersection. Two antiparallel forces of the same magnitude applied on a rigid body at different points forms a pair of forces. A pair of forces is the simplest system of forces that cannot be replaced by a single force. This fact can also be demonstrated with the apparatus. If we choose the weights in the suspension such that the force F1 is equal to the weight G, we will not able to find a force balancing the pair of forces. By applying the results obtained in these examples, we can determine the superposition of forces acting on a rigid body in the general case. Let F1 P1, F2 P2, ellipsis, Fn Pn be the forces acting on a rigid body at the points P1, P2, ellipsis, Pn. For the sake of simplicity, only the first two forces are shown in the figure. Now we apply the forces F1O, minus F1O, F2O, minus F2O, ellipsis, Fno, minus Fno at an arbitrary point O of the body. Here we also show only the first two pairs of the opposite forces. Since these forces cancel each other out, they have no effect on the rigid body. Then we determine the net force Fo of the forces F1O, F2O, ellipsis, Fno, which is applied at the point O. The net force F can be translated along its line of action and we write it without specifying the point of application. The rest of forces forms the pairs of forces F1 P1, minus F1O, F2 P2, minus F2O, ellipsis, Fn Pn, minus Fno. As a result, we replace the system of forces acting on the body with a single force and n pairs of forces. This procedure does not simplify the system of forces applied on a rigid body, but we will prove that the pairs of forces acting on the body can be reduced to a single pair of forces, and in turn, a general system of forces can be reduced to a single force and a single pair of forces. Now we introduce a new quantity called torque acting on a rigid body about an axis. Let us consider a rigid body rotating about a fixed axis as seen in the figure. For a vertical axis of rotation, we can neglect the effects of the weight of the body on its motion. As everyday experience shows, we can change the state of motion of such a body, for example when we open or close a door, by applying a force on it provided the line of action of the force is not parallel with the axis of rotation. In other words, if an arbitrary force F' is exerted upon a rigid body rotating about a fixed axis, only its component F lying in the plane perpendicular to the axis of rotation can have an effect on the rotation of the body. Then we can examine a force F acting on a body with the line of action in the plane perpendicular to the axis of rotation passing through the plane at the point O. Everyday experience also shows that the force F can only have effect on the rigid rotation if its line of action and the axis of rotation do not intersect, that is the distance d between the point O and the line of action of the force does not vanish. The perpendicular distance d from the axis to the line of action of the force F is called the lever arm of the force F about the axis of rotation. We define the torque tau of the force F acting in the plane perpendicular to the axis of rotation by the magnitude of the force F times the lever arm d of the force. By convention, counterclockwise torques are positive and clockwise torques are negative. The unit of torque is given by the unit of force times the unit of length, which is the same as the unit of work, that is the unit of mass m times the unit of length L times the unit of time t to minus 2, times the unit of length L. The SI unit of torque is therefore equal to Newton meter. We can perform the following experiment with a spool rolling on the floor to demonstrate the importance of the relative position of the line of action to the instantaneous axis of rotation for the effect of the force acting on the rotating body. We can pull the thread wound on the spool such that the angle measured between the direction of the line of action and the floor is either greater or smaller than a critical angle. If the force F is applied on angles below the critical angle, then the spool will roll towards the person pulling the thread. If the force F is applied on angles above the critical angle, then the spool will roll away from the person pulling the thread. In the figure, the point O denotes the contact line of the spool and the floor serving as the instantaneous axis of rotation for the spool. In the first case, the force F rotates the lever arm OP in clockwise direction about the instantaneous axis of rotation, that is the torque tau of the force F about the axis of rotation is negative. In the second case, the force F rotates the lever arm OP in counterclockwise direction about the instantaneous axis of rotation, that is the torque tau is positive. By applying the concept of torque, we can formulate the condition for the equilibrium of rigid bodies free to rotate about a fixed axis, such as levers used to multiply force. Let us suppose that a system of forces F1, F2, ellipsis, Fn is exerted on a rigid body free to rotate about a fixed axis, where the lines of action for all the forces lie in a plane or planes perpendicular to the axis of rotation. In the figure, the point O denotes the intersection of the axis and the plane or planes of the lines of action, and D1, D2, ellipsis, Dn are the lever arms of the corresponding forces about the axis of rotation. The rigid body under the influence of these forces is in equilibrium if the algebraic sum of the torques τ1, τ2, ellipsis, τn of the forces F1, F2, ellipsis, Fn about the rotation axis vanishes. Here each torque tau is given by the magnitude of the force Fi times the lever arm di of the force Fi. Archimedes' law of the lever is just a special case of this condition for n equal to 2, stating that the weights suspended from a lever are in balance at distances inversely proportional to their magnitudes. If the force F1 represents the weight suspended from the left arm of the lever at the distance d1 measured from the pivot of the lever or its fulcrum, and F2 is the weight suspended from the right arm of the lever at the distance d2 from the fulcrum, then we can write that the magnitude of the force F1 times the lever arm d1, minus the magnitude of the force F2 times the lever arm d2 vanishes. The second term in the sum is negative since the force F2 produce a clockwise torque on the lever. This formula is equivalent to the equation stating that F1 times d1 is equal to F2 times d2, which can be demonstrated with the setup shown in the figure. That is, 2 units of weight times 6 units of length is equal to 3 units of weight times 4 units of length. This law immediately follows from the result already obtained in the discussion on the superposition of forces acting on rigid bodies because the forces F1 and F2 can be replaced by the force F with a line of action passing through the point O. Since its line of action has an intersection with the axis of rotation, the net force F cannot produce rotation. Another important application of the concept of torque is related to the work done in the case of rigid rotation. If a rigid body turns through a small angle delta phi about the axis passing through the point O under the influence of the force F1 applied on the body at the point P, then the point P has a small displacement delta s given by r times delta phi, where r is the distance between the points O and P. The work delta W done by the force F can be written as the magnitude of the force F times the displacement delta s times cosine alpha, where alpha is the angle between the tangent to the circular trajectory of the point P and the line of action of the force F. This expression can be written as F times r times delta phi times cosine alpha, where r times cosine alpha is equal to the distance d between the point O and the line of action of the force F. Then the right-hand side gives the magnitude of the force F times the distance d times the angle delta phi. Since the distance d is the lever arm of the force F about the axis passing through the point O, F times d is equal to the torque tau of the force F about this axis. As a result, the work delta W done on the body by the force F can be written as the product of the torque tau and the angle delta phi. In the case depicted in the figure, this work is positive, that is, the torque tau is positive. The work done by the force minus F is negative because the torque tau is negative. If the angle delta phi tends to 0, then we obtain the infinitesimal work dW given by the torque tau times the differential of the angle phi. For a finite rotation through the angle phi, the total work done by the force F can be written as the integral of the torque tau of the force with respect to the angle phi. If the torque is constant, then the work W is simply equal to the torque tau times the angle phi. Now we generalize the concept of torque about a point and interpret it as a vector quantity. Let us suppose that a rigid body is free to rotate about the point O, and the force F is applied on the body at the point P. If theta denotes the angle between the direction of the position vector r of the point P with respect to the point O and the line of action of the force F, then the lever arm d of the force F about the point O can be written as the length of the position vector r times sine theta. By definition, the torque tau of the force F about the instantaneous axis of rotation passing through the point O is given by the magnitude of the force F times the lever arm d of the force, which is equal to r times F times sine theta. If we interpret the right-hand side as the magnitude of a cross product, namely the cross product of the position vector r and the force F, then we can generalize the concept of torque as follows. The torque tau of the force F applied at the point P about the point O is defined by the cross product of the position vector r of the point P with respect to the point O and the force F. Since the cross product of two vectors also gives a vector, torque is defined as a vector. Its direction perpendicular to the plane spanned by the vectors r and F, and its orientation is determined by the right-hand rule. The unit of torque is the unit of length times the unit of force as stated in the definition of the scalar-valued torque. That is the unit of mass m times the unit of length L times the unit of time t to minus 2, times the unit of length L, which has the SI unit of Newton meter. We can attach a Cartesian coordinate system to the center of rotation O where the instantaneous axis of rotation is the z-axis. Then we can write the x component of the torque tau about the center of rotation as the y coordinate of the point of application P times the z component of the force F applied at the point P, minus the z coordinate of the point P times the y component of the force F. Similarly, the y component of the torque tau is given by the difference between the z coordinate of the point P times the x component of the force F, and the x coordinate of the point P times the z component of the force F. Finally, the z component of the torque tau is equal to x times Fy, minus y times Fx. By applying the definition of torque as a vector, we can also state that the torque of an arbitrary force F about an axis passing through the point O is given by the component of the torque tau parallel with the axis of rotation. Since we have chosen the Cartesian coordinate system such that its z-axis is the instantaneous axis of rotation, the torque of the force F about the z-axis passing through the point O is equal to the z component of the torque tau, which can be written as the z component of the cross product of the position vector r of the point of application P and the force F. In other words, it is given by the x coordinate of the point P times the y component of the force F, minus the y coordinate of the point P times the x component of the force F. If the line of action of the force F exerted on the body is in the xy plane or in any plane parallel with the xy plane, then the z component of the torque tau can be written in the form introduced in the scalar definition of torque. For the z-axis as the axis of rotation and the x-axis perpendicular to the line of action of the force, the x component of the force F vanishes. As a result, the formula describing the z component of the torque reduces to the product of the x coordinate of the point of application P and the y component of the force F. For example, let us apply the forces F1 and F2 at the points P1 and P2 such that their lines of actions are perpendicular to the x-axis. Then the z component of the torque tau1 of the force F1 is given by the coordinate x1 of the point P1 times the y component of the force F1. Since x1 is equal to minus the lever arm d1 and f sub 1 y is equal to minus the magnitude of F1, we obtain F1 times d1, which is positive, indicating a counterclockwise rotation. The z component of the torque tau2 of the force F2 is given by the coordinate x2 of the point P2 times the y component of the force F2. Here x2 is equal to the lever arm d2 and f sub 2 y is equal to minus the magnitude of the force F2. Then tau z can be written as minus F2 times d2, which is negative, indicating a clockwise rotation. We also note that neither the z component of the force, nor the z coordinate of the point of application appear in the expression describing the z component of the torque tau. This involves the previously mentioned fact that neither the component of a force parallel with the axis of rotation, nor the coordinate of the point of application of the force specifying its position along the axis have a role in the rotation about the axis. By applying the general definition of torque, we can formulate the condition of equilibrium for a rigid body free to rotate about a single fixed point. Let us consider an experiment where we stick a solid cylinder upon a rod tapered to a point, as seen in the figure. If the diameter of the rod is smaller than the one of the bore at the bottom of the cylinder, then the tip of the rod is only one contact point with the cylinder denoted by the letter O. As a result, the cylinder is free to rotate about the contact point O, which is a fixed point of the rigid body and also called pivot point. Since the rod is in a vertical position, the cylinder is subjected to only its own weight and stays at rest. If we apply the force F1 on the cylinder at the point P1 described by the position vector R1, the body will turn about an axis passing through the pivot point O. However, by applying one or more forces on the body, for example the forces F2 and F3 with the points of application P2 and P3 described by the position vectors R2 and R3 respectively, we are able to maintain the equilibrium of the cylinder. We can perform an experiment with dynamometers attached to the points P1, P2 and P3 of the body and measure both the magnitudes and the directions of the forces applied on the body while it stays at rest. If the cylinder is in equilibrium for given position vectors R1, R2 and R3 of the points of application of the forces F1, F2 and F3 with respect to the pivot point O, then the experiment can demonstrate that the cross product of R1 and F1, plus the cross product of R2 and F2, plus the cross product of R3 and F3 vanishes. By definition, the cross products on the left-hand side of the equation are the torques τ1, τ2 and τ3 of the forces F1, F2 and F3 applied at the points described by the position vectors R1, R2 and R3. The condition therefore states that the vector sum of these torques must vanish in equilibrium. The general formulation of this condition, which can also be demonstrated by experimentally for a finite number of forces, is the following. For a system of forces F1, F2, ellipsis, Fn applied on a rigid body free to rotate about a pivot point O, the body is in equilibrium if the vector sum of the torques τ1, τ2, ellipsis, τn about the pivot point O vanishes. Here the torque τi for all I from 1 to n, is equal to the cross product of the position vector Ri of the point Pi with respect to the pivot point O, and the force Fi applied at the point Pi. In this condition, the reference point O is the pivot point, that is a fixed point of the rigid body around which the body is free to rotate. However, we can also choose an arbitrary reference point O' in the body, and write the torque τi in the terms of the position vector R'I with respect to the new reference point for all I from 1 to n. Then we can write the vector sum in the condition as the sum of the cross products of the position vectors R'I and the forces Fi from I equals 1 to n, where each vector R'I can be written as the vector sum of the vector R0 and the original position vector Ri. As the figure shows, R0 denotes the vector pointing from the new reference point O' to the pivot point O. The right-hand side can be written as the sum of the cross product of the vector R0 and the force Fi from I equals 1 to n, plus the sum of the cross product of the vector Ri and the force Fi from I equals 1 to n. The second sum is simply the original sum appearing in the condition. Since the vector R0 does not depend on the index I, it can be factored out in the first sum. Then we obtain the cross product of the vector R0 and the net force F acting on the body defined by the vector sum of the forces Fi for all I from 1 to n. This result shows that the net torque on a rigid body by a system of forces is only independent of the reference point, if those forces result in zero net force. We can apply these results to determine the torque of a pair of forces or a force couple. Let us suppose that the force couple F and minus F is exerted on a rigid body at the points P1 and P2, where the body is free to rotate about its pivot point O. Here R1 and R2 denote the position vectors of the points of applications for F and minus F with respect to the center of rotation O. The torque τ of the force couple about the pivot point O is given by the vector sum of the torques of the forces F and minus F about the point O, which can be written as the cross product of the position vector R1 and the force F, plus the cross product of the position vector R2 and the force minus F. Since the cross product is linear, the second term is equal to minus the cross product of R2 and F. Then we obtain the cross product of R1 minus R2 and F. The difference between the position vectors R1 and R2 denoted by R is equal to the vector pointing from the point of application P2 of the force minus F to the point of application P1 of the force F. As a result, we can write the torque τ of the pair of forces as the cross product of the vector R and the force F, which is independent of the position of the reference point O. The direction of the torque is perpendicular to the plane of the pair of forces with the orientation determined by the right-hand rule of the cross product, and its magnitude is given by the magnitude of the force F, times the length of the vector R, times the sine of the angle theta between the vectors R and F. Since the length of the vector r times sine theta gives the distance d between the lines of actions of the forces, we can state that the magnitude of the torque of a pair of forces is equal to the magnitude of any of the forces in the pair, times the distance between the lines of actions of the force couples. Only the magnitude and the direction of the torque determined by the cross product are relevant to the effect of the pair of forces on the rotation of the rigid body. The points of applications of the force couple in the individual quantities r, F and -F do not play any role in the effect. In other words, two pairs of force are equivalent if their torques have the same magnitude and direction. For example, let us consider the force couple F and -F applied at the point P1 and P2 of a rigid body. By introducing the auxiliary forces F' and -F' cancelling each other out, we can derive the pair of forces F1 and -F1 as the vector sums of the first force couple and the auxiliary forces. The force couple F and -F applied at the points P1 and P2 is equivalent with the force couple F1 and -F1 with the same points of application because the auxiliary forces do not have contribution to the torque of the force couple. If we translate the pair of forces F1 and -F1 such that their points of application are at the points Q1 and Q2, then the force couple F1 and -F1 applied at the points Q1 and Q2 is still equivalent with the original force couple. This can be seen from the fact that the magnitude of the force F times the distance d between the lines of actions of the forces F and -F is equal to the magnitude of the force F1 times the distance d1 between the lines of actions of the forces F1 and -F1. We can even talk about the equivalence of force couples in a more general case. Two force couples having the same torque are equivalent even if their lines of actions lie in two distinct parallel planes. This statement is illustrated by the experiment with the apparatus shown in the figure. A thick beam is suspended from three wires passing through fixed pulleys and held in equilibrium with the weights G1, G2 and G3 hanging on the other ends of the wires. The weight G2 is connected to a rod by the wire and the rod attached to the beam. Two further weights are suspended from the beam and another rod attached to the beam in order to produce force couples acting on the beam. As we can see, two sets of weight are used in the series of the weights G1, G2 and G3, light ones and heavy ones. The light weights are only applied to achieve complete balance of the net forces exerted on the beam, and their contribution to the effect of the heavy weights is negligible. In this setup, two force couples are exerted on the beam, the force couple F1 and -F1, and the force couple F2 and -F2. Since the beam is in equilibrium under the influence of the two force couples and the net force of the force couples vanishes, the net torque rotating the beam must vanish as well. This can immediately be seen if we determine the torques due to the two force couples. The magnitude of the torque τ1 produced by the pair of forces F1 and -F1 acting on the beam is equal to the magnitude of the force F1 times the distance d1 between the lines of action of the forces F1 and -F1. As the figure shows, its value is given by 2 units of weight times 6 unit of length. By definition, the torque τ1 is perpendicular to the plane P1 spanned by the force couple F1 and -F1, and its orientation is given by the right-hand rule producing a clockwise rotation. The magnitude of the torque τ2 produced by the force couple F2 and -F2 acting on the beam is equal to the magnitude of the force F2 times the distance d2 between the lines of action of the forces F2 and -F2. Its value is given by 4 units of weight times 3 units of length. The torque τ2 is perpendicular to the plane P2 of the force couple F2 and -F2, and its orientation shows that it produces a counterclockwise rotation. Since the planes P1 and P2 are parallel, the torques τ1 and τ2 are opposite in direction. At the same time they have the same magnitude, that is the torque τ1 is equal to minus the torque τ2. Then the torque due to the pair of forces F1 minus F1 is compensated by the torque due to the force couple F2 minus F2 as we expected for the system in equilibrium. The equilibrium of the beam shows that the effect of the force couple F2 and minus F2 is equivalent to the one of the force couple F3 minus F3. The pair of force F3 and minus F3 can compensate the effect of the force couple F2 and minus F2 because they have the same points of applications while point in opposite directions, and their torques are equal in magnitude but opposite in direction. Indeed, the magnitude of the torque τ3 due to the pair of forces F3 and minus F3 is given by the magnitude of the force F3 times the distance d2 of the line of actions of the force couple, or 4 units of weight times 3 units of length. The torque τ3 is perpendicular to the plane P2 of the forces F3 and minus F3, and its orientation shows that it produces a clockwise rotation. The torques τ1 and τ3 therefore have the same magnitude and direction, that is the torque τ1 is equal to the torque τ3. In the experiment, we have demonstrated that the force couple F2 and minus F2 lying in the plane P1 is equivalent to the force couple F3 and minus F3 lying in the plane P2 parallel with the plane P1. This result shows that only torque has a role in the effect of a force couple, and this effect will not change if the torque is translated parallel to itself. In other words, the starting point of the torque vector can be translated to an arbitrary point of the rigid body. Such a vector is called free vector as opposed to the bound vectors like the position vector, which cannot be translated. Then we conclude the theorem stating that a system of force couples acting on a rigid body is equivalent to a single force couple having the torque given by the vector sum of the torques due to the individual force couples. Here the net torque and the torques due to the force couples are determined with respect to a given reference point. We can apply this theorem to another one on the reduction of a general system of forces. When we studied the superposition of forces applied on a rigid body, we demonstrated that a system of n forces acting on the body can be replaced with a single resultant force and n pairs of forces or force couples. Now the theorem formulated here states that these n force couples Fi applied at the point Pi and minus Fi applied at a reference point O for I from 1 to n, are equivalent to a single force couple having the torque tau given by the vector sum of the torques of the individual force couples. That is, tau is equal to the sum of the cross products of the vectors Ri and Fi, where I is the vector pointing from the point of application Pi of the force Fi to the reference point O. Then we can state the following theorem. The system of forces F1, F2, ellipsis, Fn acting on a rigid body is equivalent to the net resultant force F and a force couple producing the torque tau. Here the resultant force F is given by the vector sum of the forces Fi from I equals 1 to n, and it can be applied at an arbitrary point O of the body. The torque tau due to the force couple is equal to the sum of the cross product of the vector Ri and the force Fi from I equals 1 to n. In the vector products, Ri is the position vector of the point of application Pi of the force Fi with respect to the point O. We note that the resultant force F and the torque tau can be combined into a pair of vectors called wrench forming a six-dimensional vector used in screw theory, a mathematical formulation of forces and torques acting on rigid bodies. Then the theorem states that a system of forces acting on a rigid body can be replaced by a wrench. As already stated, the starting point of the torque vector tau due to the force couple can be at an arbitrary point of the body. We have also shown that the choice of another reference point O' still gives the same net force F but results in a different torque tau prime. The torque is given by the sum of the cross product of the position vector Ri' and the force Fi from I equals 1 to n, where I' is the position vector of the point of application Pi of the force Fi with respect to the new reference point O'. We proved that this vector sum can be written as the cross product of the vector R0 pointing from the new reference point O' to the reference point O and the net force F, plus the sum of the cross product of the position vector Ri and the force Fi from I equals 1 to n. Since the second term is just the torque tau, we see that tau prime and tau are generally different. As the figure shows, we can always find a new reference point O' such that the net force F and the net torque tau have the same direction, that is the net force is perpendicular to the plane of the net force couple. We can determine the cross product of this equation with the resultant force F for the torque tau prime parallel with the force F. Then the cross product of tau prime and F in the left-hand side vanishes, and the cross product of F and the right-hand side of this vector equation can be transformed into a linear system of the coordinates of the vector R0 describing the point O'. If we determine the components of the resultant force F and the net torque tau for a given reference point O, the linear system can be solved for the coordinates of the vector R0, and we can compute the torque tau prime parallel with the force F. Now we introduce the concept of centroid, which is usually defined as the geometric center of a plane figure or a solid figure, but it has an important role in the study of forces acting on rigid bodies as well. First, let us consider the simplest idealized rigid system, the rigid rotor. It is the model of a rotating dumbbell that consists of two solid spheres connected with a rigid stick holding them a fixed distance apart. We approximate the spheres by the point masses m1 and m2 at their centers p1 and p2, and assume that the mass of the stick is negligible. The gravitational forces acting on this system are given by the weights g1 and g2 of the 2 point masses, which are equal to the mass m1 times the gravitational acceleration g and the mass m2 times the acceleration vector g, respectively. The weights g1 and g2 point downward towards the center of Earth, but the lines of action of the two forces can be considered parallel over a short distance determined by the size of the rigid rotor. We have already shown that these parallel planar forces can be replaced by their resultant force capital G, that is the vector sum of g1 and g2, where the magnitude of capital G is equal to the sum of the masses m1 and m2 times the magnitude of the gravitational acceleration g. We also saw that the line of action of the resultant force passing through the section P1 P2 at the point C is parallel with the lines of actions of the two forces, and its distance from them is given by the equation stating that the ratio of the distance d1 between the points P1 and C to the distance d2 between the points P2 and C is equal to the ratio of the magnitudes of the two forces, that is the ratio of the mass 2 to the mass m1. This relation between the two fractions can also be written as the equation stating that m1 times d1 is equal to m2 times d2. By applying the theorem of transmissibility, we can translate the point of application C of the resultant force along its line of action. In other words, the point of application can be any point in the stick along the line of action of the force G. However, if we rotate the body and change its orientation, the line of action of the force still passes through the point C. The point C can therefore be considered as the point of application of the weight G of the body, and we call it the centroid of the rigid rotor. We can generalize this method for any rigid body in a homogeneous gravitational field because the gravitational forces acting on the particles of the body are parallel with each other and they can be reduced to a single force, the weight G of the body. Then the centroid of a rigid body introduced most likely by Archimedes, is the point where the line of the action of the weight G always passes through, regardless of the orientation of the body. If a rigid body is supported at its centroid, then the effect of the weight G of the body is compensated by the constrained force due to the support. In other words, a rigid body supported at its centroid is in equilibrium under the influence of gravity, regardless of the orientation of the body. We already demonstrated that the net torque produced by the forces acting on a body vanishes if the body is in equilibrium. Therefore, the torque acting on a rigid body produced by its own weight vanishes with respect to its centroid, regardless of the orientation of the body. In order to determine the centroid of a relatively small body, we can apply the method where we first suspend the body at a point P1 from a wire, then we suspend it at another point P2. In both the cases the body is in equilibrium, in which the vertical lines M1 and M2 called medians passing through the point of suspension also pass through the centroid C of the body. Otherwise the torques produced by the weight G acting at the point C with respect to the points P1 and P2 did not vanish, and the body were not in equilibrium. Then the centroid C of the body is the point of intersection of the medians M1 and M2 determined by suspending the body at its two different points P1 and P2. In many cases we can determine the centroid of homogeneous bodies based on their symmetry properties. For example, in the case of a homogeneous thin rod, disk, annulus in a plane or torus in space, sphere or cylinder, the centroid is the geometric center of the body. As the example of the annulus or the torus shows, the centroid of the body is not necessarily located in the body. Generally, if a homogeneous body is symmetric about a plane, a line or a point, then the centroid is in the symmetry plane, on the symmetry line or at the symmetry point. If the body has more than one symmetry planes or symmetry lines, then the centroid lies on the line of intersection of these planes or at the point of intersection of these lines. For example, the centroid of a homogeneous triangle is the point of intersection of its three medians connecting the vertices of the triangle to the midpoints of the opposite sides. We saw that the method used to determine the centroid of a rigid rotor can also be applied in the case of solid bodies. Now we generalize this method for rigid bodies of whatever shape, with no symmetry at all. Let us consider a rigid body that consists of the endpoints masses m1, m2, ellipsis, mn. For the sake of simplicity, we show only the first three point masses in this system and omit the rigid sticks holding them fixed distances apart. We can construct the centroid of this rigid system of point masses by repeating the method applied for the rigid rotor. First we determine the centroid C sub 1 2 of the point masses m1 and m2, then we combine these point masses into the point mass m1 plus m2 at their centroid. The position of the point C sub 1 2 lying on the line section connecting the point masses m1 and m2 is determined by the equation stating that the mass m1 times the distance d1 between the point mass m1 and the centroid is equal to the mass m2 times the distance d2 between the point mass m2 and the centroid. In the second step we determine the centroid C sub 1 2 3 of the combined point mass and the point mass m3, and we combine them into the point mass m1 plus m2 plus m3 at the centroid C sub 1 2 3. Then the equation determining the position of the centroid on the line section connecting the combined point mass m1 plus m2 at the point C sub 1 2 and the point mass m3 is the following. The sum of the masses m1 and m2 times the distance d sub 1 2 between the point C sub 1 2 and the point C sub 1 2 3, is equal to the mass m3 times the distance d3 between the point mass m3 and the centroid c sub 1, 2, 3. We can continue this procedure for the rest of the rigid system of point masses, and determine the centroid of the whole system. For a given reference point O, the set of position vectors R1, R2, ellipsis, Rn describe the positions of the point masses in the system. Let R sub 1, 2 denote the position vector of the centroid C sub 1, 2, where the lengths of the vectors R sub 1, 2 minus R1 and R2 minus R sub 1, 2 give the distances d1 and d2 respectively. Then we can write the first equation under the figure in the form stating that the mass m1 times the difference between the vectors R sub 1, 2 and R1, is equal to the mass m2 times the difference between the vectors R2 and R sub 1, 2. We can use the vector equation instead of its scalar projection because the vectors R sub 1, 2 minus R1, and R2 minus R sub 1, 2 have the same direction. By removing the parentheses and transposing the negative terms to the opposite sides of the equation, we obtain the expression stating that m1 times R sub 1, 2 plus m2 times R sub 1, 2, is equal to m1 times R1 plus m2 times R2. Now we can express the position vector of the centroid C sub 1, 2 as the sum of m1 times R1 and m2 times R2, divided by the sum of m1 and m2. We can follow the same procedure for the second step. If R sub 1, 2, 3 denotes the position vector of the centroid C sub 1, 2, 3, then the lengths of the vectors R sub 1, 2, 3 minus R sub 1, 2 and R3 minus R sub 1, 2, 3 give the distances d sub 1, 2 and d3 respectively. We can apply this notation and write the second equation under the figure in the following form. The combined mass m1 plus m2 times the difference between the position vectors R sub 1, 2, 3 and R sub 1, 2, is equal to the mass m2 times the difference between the position vectors R3 and R sub 1, 2, 3. By removing the parentheses and transposing the terms with the negative sign to the opposite side of the equation, we obtain an equation stating that the sum of m1 and m2 times R sub 1, 2, 3, plus m3 times R sub 1, 2, 3 is equal to the sum of m1 and m2 times R sub 1, 2, plus m3 times R3. Now we substitute R sub 1, 2 obtained in the previous step into this equation, and express R sub 1, 2, 3 from it. As a result, the position vector of the centroid C sub 1, 2, 3 can be written as the sum of m1 times R1, m2 times R2 and m3 times R3, divided by the sum of m1, m2 and m3. If we continue this iterative procedure for the rest of the point masses in the system, we can determine the position vector Rc of the centroid for the rigid system of the point masses m1, m2, ellipsis, mn at the points given by the position vectors R1, R2, ellipsis, Rn with respect to the reference point O. Then the centroid Rc can be written as the sum of the mass mi times the position vector Ri from I equals 1 to n, divided by the sum of mi from I equals to n. Since the sum in the denominator gives the total mass m of the rigid system, the position of the centroid is given by 1 over the total mass m, times the sum of the mass mi times the position vector Ri from I equals 1 to n. In order to provide a quantitative description of the position of the centroid of a system of point masses, we introduce a Cartesian coordinate system having its origin at the reference point O, and represent the position vector Ri of any point mass mi in the system by the Cartesian coordinates xi, yi and zi. Then the coordinate expansion of the vector equation describing the position vector Rc of the centroid C gives three component equations. The x-coordinate of the centroid is equal to 1 over the total mass m of the system, times the sum of the mass mi times the coordinate xi from I equals 1 to n. We have similar equations for the y and z components of the centroid as well. The vector and the component equations define the centroid of a system of point masses even if the point masses have no rigid connections with each other. Although the three component equations of the centroid depend on the coordinates of the point masses, it is evident from the first part of the iterative construction method without using any reference point and coordinate system that the position of the centroid of the system with respect to the system itself is independent of the choice of the coordinate system. The position of the centroid of a system of point masses or a rigid body is completely determined by the distribution of the mass in the system or over the volume of the body. In the general case when the distribution of mass is arbitrary, we will therefore call the centroid the center of mass of a system of point masses or a rigid body. Then the centroid is equivalent to the geometric center of a body, whereas its center of mass is defined by the equations obtained for the position vector Rc and its coordinates. For homogeneous bodies or point masses arranged in a symmetric manner, the centroid is the same of the center of mass. In this example we consider 4 point masses m at the corners of a square. Due to the symmetry of the distribution of this arrangement, the center of mass of the system is at the geometric center C of the square, that is the center of mass of the system and the centroid of the square coincide. However, if we double the mass of the point masses at the lower left and right corners of the square, the center of mass Cm of the system is no longer at the centroid C of the square. Cm will be located at a point on the vertical axis of symmetry of the square that is closer to the more massive point masses. We can also determine the center of gravity of a system of point masses if we combine the weights of the point masses instead of their masses at their center in each step of the iterative method. Then the position vector RC describing the center of gravity is given by the sum of the magnitude of the weight Gi of the point mass Mi, times the position vector Ri of the point mass from I equals 1 to n, divided by the magnitude of the total weight G of the system of the point masses. Here the magnitude of the weight Gi is equal to the mass Mi times the magnitude of the gravitational acceleration G, and capital G denotes the total weight of the system, that is the product of its total mass m and the magnitude of the gravitational acceleration G. As a result, while the center of mass of a rigid body is independent of gravity, the center of gravity depends on the gravitational field acting on the body. As opposed to a system of individual point masses, ordinary bodies have continuous distribution of mass which can be either homogeneous or inhomogeneous. In order to determine the center of mass Cm of a rigid body, we break up the body into n volume elements delta Vi, where I denotes the position vector of the volume element delta Vi with respect to a reference point O. The mass element delta Mi is equal to the mass of the matter in the volume element of body with a continuous distribution of mass. Then we can apply the formula derived for a system of point masses and approximate the center of mass Rc of the body with the sum of the position vector Ri times the mass delta Mi from I equals 1 to n, divided by the sum of delta Mi from I equals 1 to n. Since the density ρI of the matter in the volume element delta Vi is given by the ratio of delta Mi to delta Vi, we can express delta Mi as the product of ρI and delta Vi. The center of mass Rc of the body can therefore be approximated with the sum of ρI times delta Vi from I equals 1 to n, divided by the sum of ρI times delta Vi from I equals 1 to n. If delta Vi tends to 0 while the number n of the volume elements approaches infinity, the limit of each sum in the fraction gives a volume integral over the volume of the body. As a result, the position vector Rc of the center of mass of a rigid body that has a density ρ depending on the position vector r, is given by the volume integral of the density ρ times the position vector r with respect to the reference point r over the volume integral of the density ρ. Here the integral of the density ρ over the total volume of the body gives the total mass m of the body, and the position vector Rc can be written as 1 over the mass m times the volume integral of the density ρ times the position vector r. If we attach a Cartesian coordinate system to the reference point O, we can express the x-coordinate of the center of mass by 1 over the mass m times the volume integral of the density ρ times the x-coordinate. We have similar equations for the other two Cartesian coordinates as well. As an example, let us determine the center of mass for a homogeneous right circular cone with the radius of its base r and height h. Since the conic solid is homogeneous, its density ρ is constant. We attach a two-dimensional Cartesian coordinate system to the vertex of the cone such that its x-axis coincides the symmetry axis of the cone, and its y-axis is parallel with the base of the cone. Due to the symmetry and the homogeneity of the cone, its center of mass must located at its axis of symmetry, that is the y and z coordinates of the center of mass vanish. Then we only need to compute the x-coordinate of the center of mass of the cone. By applying the volume integral of ρ times x over the mass m of the cone obtained for the coordinate xc, we can determine the position of the center of mass on the x-axis. Let us consider a disk that has the radius y and the infinitesimal width dx at the distance x from the vertex, as seen in the figure. Such a disk parallel with the base of the cone is an infinitesimal volume element dv of the cone given by the area of its base times its width, that is y squared times pi times dx. The figure shows that the ratio of y to x is equal to the ratio of r to h, and y squared can be expressed as the square of the ratio of x times r to h. Then the volume element dv is given by the ratio of r squared times pi to h squared, times x squared times dx. If we substitute this expression into the volume integral over the whole cone, then we can transform it into an integral with respect to the x-coordinate from 0 to the height h of the cone. As a result, the coordinate xc is equal to 1 over m times ρ times the ratio of r squared times pi to h squared, times the integral of x cubed with respect to x from 0 to h. By performing the integration we obtain h to the fourth over 4, and we can write the right-hand side in as 1 over m times ρ times the ratio of r squared times pi times h to 3, times 3 times h over 4. Since the ratio of r squared times pi times h to 3 is equal to the total volume v of the cone, and the density ρ times the volume v gives the mass m of the solid body, the x-coordinate of the center of mass of the homogeneous cone is given by 3/4 times the height h of the cone. We immediately see from this calculation that an inhomogeneous cone may have a different center of mass. For example, if the density of the solid is proportional to the x-coordinate, that is, the density is given by ρ times x, then we need to integrate x to the fourth power instead of x cubed, which gives h to the 5/5. Then the final result is equal to 3/5 times h squared instead of 3/4 times h obtained for the homogeneous cone. Further properties of the center of mass can also be presented demonstrating the usefulness of this concept in the dynamics and statics of rigid bodies. We have already seen that the weight G of a rigid body has a line of action that always passes through the centroid or the center of mass C of the body. Here the weight G is given by the mass m of the body times the gravitational acceleration g. As a result, the center of mass of a rigid body of weight m times g can be considered as the point of application of the gravitational force m times g, irrespective to the orientation of the body. By supporting a rigid body at its center of mass, we compensate its weight, that is the gravitational force acting at this point, and the body will be in equilibrium. These properties of the center of mass are very important if we want to determine the work done by the gravitational force, because a rigid body of mass m can be replaced by a point mass m located at the center of mass of the body. If we suppose that the vertical position of the center of mass C of a rigid body is increased by the height delta h, we can express the work W done against the gravitational force, that is the increase in the potential energy of the body delta E pod, as the mass m of the body times the magnitude of the gravitational acceleration times delta h. We also saw that the torque due to the weight of a rigid body vanishes with respect to its centroid or center of mass and does not rotate the body. If the body is supported at its center of mass but it is free to rotate, then we can determine the axis about which the rigid body will rotate under the influence of a force couple. We already presented an experiment where a board is placed on 3 balls of the same size such that the balls rolling on the floor allow the board to move horizontally. If we apply the force couple F and minus F on the board at the points P1 and P2, then the board will rotate in the horizontal plane, and we can demonstrate that the vertical line passing through the center of mass of the board is the axis of rotation. In general, a force couple applied on a free rigid body will rotate the body about an axis passing through the center of mass of the body, but the direction of the rotation depends on both the torque due to the force couple and the distribution of matter in the body. Now we formulate the general criteria for the equilibrium of a rigid body. We have already shown that a system of forces F1, F2, ellipsis, Fn applied at the points given by the position vectors R1, R2, ellipsis, Rn relative to an arbitrary point O of the body can always be reduced to 2 set of quantities. The first set consists of a single vector, a resultant or a net force F given by the vector sum of the forces Fi from I equals 1 to n, which is applied at the point O. The second set is a force couple producing the torque tau given by the sum of the vector products of the position vectors Ri and the forces Fi, from I equals 1 to n. The force F acting at the point O can be replaced by the force acting at the center of mass C of the body and the force couple F and minus F acting at the points O and C. Then the force couple on its own would produce a rotation about an axis passing through the center of mass C of the body, and the resultant force F on its own would produce both a translation and a rotation about an axis passing through the center of mass C. It follows from these statements that in equilibrium both the force F and the torque tau must equal to 0. We can conclude that a rigid body is in equilibrium if the resultant force F of all the forces acting on the body and the net torque tau of the torques produced by these forces with respect to an arbitrary point vanish. In that case we can say that the forces acting on the rigid body are balanced. Here we can talk about the torque with respect to an arbitrary point, since we already proved that if the net force F vanishes and the net torque tau with respect to a given point is 0, then the net torque with respect to any other point is also 0. We note that the forces acting on a rigid body can be both unconstrained forces such as the weight of the body, and constrained forces, for example the support or the suspension of the body, since the criteria for the equilibrium of rigid bodies do not make any distinction between them. Now we examine and interpret the equations describing the criteria of equilibrium of rigid bodies. The first criterion of equilibrium can be illustrated by the statement that the polygon of forces constructed from the vectors representing the n forces Fi acting on the body regardless to their points of application, must be closed if the body is in equilibrium. This construction can also be done for the second criterion with the torques tau I produced by the forces Fi, where the polygon of the n vectors tau I must be closed for a rigid body in equilibrium. The two equations describing the criteria of equilibrium of a rigid body have a fundamental importance in statics. The first equation is also known as the criterion of the translational equilibrium of a rigid body, because the body either stay at rest or perform a rectilinear motion if the net force acting on it vanishes. The second equation is called the criterion of the rotational equilibrium of a rigid body, since the sum of the torques produced by the forces at any point of the body is zero and the body is not rotating. Then we can say that a rigid body is in static equilibrium if it is in both translational and rotational equilibrium. These two vector equations can be expressed as six scalar equations of the components of the vector quantities in a Cartesian coordinate system. The six equations allow us to determine six unknown quantities, for example the components of forces or the coordinates of the points of applications of forces. The first three scalar equations describing the criterion of the translational equilibrium of a rigid body state that the sum of the x, y and z components of the forces Fi acting on the body from I equals 1 to n vanishes. The second set of the scalar equation are the components of the equation describing the criterion of the rotational equilibrium of the body. The x component of the vector equation states that the sum of the y coordinate of the point of application of the force Fi times the z component of the force Fi, minus the zi coordinate of the point of application of the force Fi times the y component of the force Fi from I equals 1 to n vanishes. The other two equations for the y and z components of the vector equation can be derived by applying a cyclic permutation of the Cartesian indices x, y and z. We already determined the criterion of equilibrium for a rigid body free to rotate about a fixed axis or a fixed point. In the case of a fixed axis, the equation describing the equilibrium of the body states that the sum of the z components of the torques tau I produced by the forces Fi acting on the body from I equals 1 to n is 0, where the z-axis is the axis of rotation. This case involves only one equation, the z component of the second vector equation. In the case of the fixed point, the equation describing the equilibrium of the body states that the vector sum of the torques tau I produced by the forces Fi acting on the body from I equals 1 to n is 0. This is the vector equation describing the criterion of the rotational equilibrium of the body when no constrained forces are applied on the body, and it is given by the three component equations. There is no contradiction between these two cases and the criteria presented here, since the remaining five equations for the first case or three equations for the second one allow us to determine the constraint or reaction forces when we fix the point or the axis of rotation. For example, let us consider a horizontal thin beam supported at 2 points, where the only unconstrained force acting on the beam is its own weight g having the point of application at the center of mass c of the beam. The forces F1 and F2 exerted on the beam by the two pin supports at the distances d1 and d2 from the center of mass c are the constrained forces acting in the system. In a Cartesian coordinate system attached to the point of application of the force F1 where the x-axis is parallel with the beam, the y and z coordinates of the points of application of the constrained forces vanish. The x components of the position vectors pointing from the center of mass c to the points of applications of the forces F1 and F2 are given by minus d1 and d2, respectively. Since all the forces acting on the beam are parallel with the y-axis, their x and z components vanish and their y components are equal to the magnitude of g, minus the magnitude of F1 and minus the magnitude of F2, respectively. As a result, the vector equation describing the criterion of the translational equilibrium of the beam has a non-vanishing y component stating that the magnitude of the weight g, minus the magnitude of the force F1, minus the magnitude of the force F2 is equal to 0. The vector equation describing the criterion of the rotational equilibrium of the beam has a non-vanishing z component, and it states that the distance d1 times the magnitude of the force F1, minus the distance d2 times the magnitude of the force F2 is equal to 0. The magnitudes of the two forces F1 and F2 can be expressed from these two equations as the ratio of the distance d2 to the sum of d1 and d2, times the magnitude of g, and the ratio of the distance d1 to the sum of d1 and d2, times the magnitude of g, respectively. These two equations show that the magnitudes of the action forces F1 and F2 or the reaction forces exerted on the two supports by the beam, are inversely proportional to the distances between their points of application and the center of mass of the beam. This result can also be derived from the principle of superposition of forces acting on a rigid body. We note that if 3 pin supports are applied for the beam instead of 2 supports, the constrained forces cannot be determined uniquely in the statics of rigid bodies. Such cases are called statically indeterminate structures with more unknown forces acting in the system than the available equations of equilibrium. When we talk about the equilibrium of a rigid body, we can distinguish between 3 different types of equilibrium. Let us suppose that a rigid body is in equilibrium, that is, the forces acting on the body are balanced. When displaced from equilibrium, the body will change its position, and the net force of the forces acting on the body and the net torque produced by these forces are not necessarily equal to zero. Then the first type of equilibrium can be described as follows. If the body under the influence of the net force and torque returns to its original equilibrium position, generally after some small oscillation about it, then the rigid body is in stable equilibrium. A typical example of such a situation is a ball at the bottom of a bowl. If the ball is displaced slightly, then it will roll back to the bottom of the bowl, that is, it will return to its stable equilibrium position. The second type of equilibrium describes a different outcome of the same initial situation. If the displaced rigid body does not return to its original equilibrium position, but moves away from it under the influence of the forces due to the displacement, then the body is in unstable equilibrium. By using the example of the ball on the bowl, we can place the ball at the top of the inverted bowl. If the ball is balanced at the top, then it is in equilibrium. However, any slight displacement causes the ball to roll down from the top of the bowl, indicating that its equilibrium position is unstable. The third type of equilibrium is perhaps the simplest one. If the displaced rigid body remains in its new position, then it is in neutral equilibrium. The ball lying on a flat surface is in a state of neutral equilibrium, since it will remain at rest even if it is slightly displaced, or it begins to move, settling in the new position if it is pushed slightly to roll. The new position of the ball is a neutral equilibrium position as well. In principle, the equilibrium of a mechanical system is stable, if the displacements in the system due to any sufficiently small interference also remain small. We have illustrated the three types of equilibrium with a ball, and any rigid body can be used as an illustration if the unconstrained force acting on the body is only its own weight. For example, we can suspend a ruler at three different points denoted by P as seen in the figure. In all the three cases, the ruler is in equilibrium because its center of mass C is on the vertical line passing through the point of suspension P, and the weight G of the ruler is compensated by the constrained force F' due to the suspension. The equilibrium of the ruler is stable, unstable or neutral depending on whether the center of mass C is below, above or at the point P. However, this criterion is not general enough, since the equilibrium of the ball used in the first example can be stable, unstable or neutral, although the center of mass of the ball is above the contact point between the ball and the surface in each case. The following criterion is still valid for both of the examples. By supposing that the unconstrained force acting on a rigid body is only its own weight, we can state that the body is either in stable or unstable equilibrium if its center of mass is in the lowest or the highest possible height. As a result of a small displacement from the stable equilibrium, the center of mass of a rigid body rises and a positive work Wg is done against the gravitational force, which increases the potential energy E pod of the body. At a stable equilibrium position, the body has therefore less potential energy than at any neighboring position occupied by the body after a small displacement. The opposite is true for the unstable equilibrium of a rigid body, where the center of mass of the body is lowered due to a small displacement of the body from its equilibrium position. Then the work done against gravity is negative, and so is the change in the potential energy, indicating that the potential energy of the body is greater at its unstable equilibrium position than at any neighboring position. In this form, the criterion can be generalized as a theorem which was stated by Lagrange in 1788 and proved by Dirichlet in 1846. The Lagrange-Dirichlet theorem states that the equilibrium position of a conservative mechanical system is stable if its potential energy assumes a local minimum in this position. In fact, the theorem only provides a sufficient but not necessary condition for stable equilibrium of a rigid body, that is, one can construct a conservative mechanical system where the potential energy has no local minimum in stable equilibrium. However, the converse of the theorem also holds for the examples from everyday life discussed here. By applying the example of the ball and the bowl, we can illustrate the theorem for the potential energy E pod of the ball as a function of the position of the ball rolling in the bowl. If we choose the bottom of the bowl as the reference level for the potential energy of the ball, then E pod is equal to 0 in equilibrium. For any displacement, the center of mass of the ball reaches a position where its height is greater than 0. Since the potential energy of the body is directly proportional to the height of the position of its center of mass, E pod is greater than 0 everywhere in the vicinity of the equilibrium position. As a result, the potential energy of the ball has a local minimum at the equilibrium position, which means it has a stable equilibrium there. If the ball is balanced on the top of the upside-down bowl, the potential energy E pod of the ball has a maximum at the top of the bowl because the height of the position of its center of mass attains the maximum. For any small displacement of the ball rolling over the bowl, the center of mass of the ball approaches the reference level. As a result, the potential energy of the ball is less than the maximum attained on the top of the bowl, and the ball has an unstable equilibrium there. In the case of neutral equilibrium, the ball can roll over a horizontal surface and its center of mass has a constant distance from the surface. Then the potential energy of the ball remains constant and the ball is in equilibrium at any position, which is a neutral equilibrium. For the sake of clarity, the reference level of the potential energy is set to be a non-zero value in the third figure. Without following the strict method elaborated by Dirichlet, we only give a sketch of the proof of the Lagrange-Dirichlet theorem. When we studied the dynamics of conservative mechanical systems, we saw that the force F acting on a point mass is given by the negative gradient of its potential energy E pot. This relationship also holds for rigid bodies under the influence of gravity, where the force F is the net force acting on the body and its potential energy can be determined from the position R of its center of mass in the gravitational field. Let the position vector R0 denote the equilibrium position of the rigid body. In equilibrium, the body is at rest and the net force F acting on it vanishes. As a result, the gradient of the potential energy of the body is equal to 0, that is, E pot has an extremum at the equilibrium position R0. We can approximate the net force acting on the rigid body by expanding the force F at a point in the vicinity of the equilibrium position R0 given by the vector sum of R0 and delta R, where the length of the displacement vector delta R is small. If we substitute the negative gradient of the potential energy E pot into the net force F, the Taylor expansion can be written as minus the gradient of E pot evaluated at the point R0, minus the second order derivative of E pot evaluated at the point R0, times the vector delta R, minus the terms of higher order in vector delta R. The first term in the right-hand side just gives the net force F acting on the body at its equilibrium position R0, which is equal to 0. We can approximate the force acting on the body up to the first order of its Taylor expansion by neglecting the terms of higher order. Then we only need to examine the sign of the second-order partial derivative of the potential energy with respect to the position R evaluated at the equilibrium position R0. If the second-order derivative of E pot is positive, then the potential energy of the body has a local minimum at the equilibrium position R0. For a negative second-order derivative, the potential energy has a local maximum at the equilibrium position. If the magnitude of the derivative is denoted by the positive constant k, then we can approximate the force F acting on the displaced body as minus or plus the constant k times the displacement delta R, depending on whether the potential energy of the body has a local minimum or maximum at the equilibrium position R0. In this result, we immediately recognize the law of force introduced in the discussion on simple harmonic motion. In the case of the local maximum of the potential energy, the force F is approximately equal to minus k times the displacement delta R, which is Hooke's law stating that the force is a linear restoring force accelerating the body in the direction opposite to the displacement and towards the equilibrium position. Since the length of the displacement vector delta R is small, the displaced rigid body undergoes a small harmonic oscillation about its equilibrium position. Normally, in realistic mechanical systems, frictional or drag forces are also exerted on the oscillating body near equilibrium and the body will dissipate its energy. Due to the loss of energy, oscillating systems have a decreasing amplitude in time, that is, the body performs a damped oscillation and eventually comes to rest at the equilibrium point. This behavior shows that the equilibrium of the body is stable if its potential energy has a local minimum at the equilibrium point. In the case of the local maximum of the potential energy, the force F is approximately equal to k times the displacement delta R, which is the other form of Hooke's law stating that the force F is a linear accelerating force and it accelerates the displaced body away from the initial equilibrium position. Then we talk about an unstable equilibrium if the potential energy of the body has a local maximum at the equilibrium point. We note that damped oscillating systems are not conservative and do not have potential energy associated with them. As a result, the equation of motion for damped oscillations must be derived from the fundamental equation of dynamics by applying Hooke's law. We can use this theorem to explain the motion of any rigid body displaced from its equilibrium position. For example, if we glue a relatively heavy fridge magnet to the inner side of a toilet paper tube and place the tube in the position on an inclined plane as seen in the figure, then it will be able to roll upward. Since the height of the common center of mass c of the weight in the tube decreases while the tube is rolling upward, the potential energy of the whole body decreases as well and attains a local minimum where the center of mass reaches its lowest possible position. Similarly, a vertical stick can be balanced on a horizontal support but it still have an unstable equilibrium because its center of mass c is above its point of support. When slightly disturbed from its position, the stick will fall down and not come back to its original position. Since the height of the center of mass of the stick decreases when the stick deviates from its vertical position, the potential energy of the stick also decreases. Consequently, the potential energy of the body has a local maximum at the vertical position of the stick. By attaching two relatively massive balls to the stick as seen in the figure, we can bring the center of mass C of the stick and the balls under the level of the support point of the stick. Then any deviation of the stick from its vertical balance position would increase the height of the center of mass and in turn the potential energy of the whole system. The equilibrium position of the stick therefore becomes stable if the stick is supplemented with the two balls. In the discussion on the conditions for stable or unstable equilibrium of rigid bodies, we always talked about the local minimum or maximum of the potential energy. Indeed, in many cases rigid bodies can have more stable and unstable equilibrium positions depending on their shape and the distribution of their mass. For example, a homogeneous solid cuboid at rest on the horizontal surface of a table is in a stable equilibrium position. Since the solid body has 6 sides, it has 6 stable equilibrium positions as well. However, the cuboid can also be balanced on its 8 vertices and 12 edges, at least in principle, and these positions can be considered as 20 unstable equilibrium positions of the solid body. This demonstrates that only the neighboring positions of the given equilibrium position are relevant in the classification of equilibrium, and we restrict our examination to the local extrema of the potential energy of a rigid body displaced from its equilibrium position. So far we always considered the effect of gravity on rigid bodies in the discussion on their state of equilibrium. Now we present 2 examples illustrating the equilibrium of a physical system where the gravitational force is not relevant. The first example is a ping-pong ball attached between 2 identical springs of negligible mass as seen in the figure. If we stretch the springs, then both of them will pull the ball by exerting forces on it, which are equal in magnitude and opposite in direction. As a result, the net force acting on the ball vanishes and the ball remains in equilibrium. For a small displacement of the ball either in vertical or horizontal direction, the ball will return to its equilibrium position with or without a damped oscillation, due to the restoring forces applied on the ball by the springs as Hooke's law states. Then the state of the ping-pong ball between the stretched springs can be described as a stable equilibrium. If we compress the springs, then both of them will push the ping-pong ball by exerting forces on it which are equal in magnitude and opposite in direction. In this case the resultant force also vanishes and the ball stays in equilibrium. However, for any displacement of the ball in the vertical direction, the springs exert an accelerating force on the ping-pong ball and push it in the direction of the displacement. The state of equilibrium of the ball between the compressed springs is therefore unstable. The next example is not a purely mechanical system since electrostatic forces play the role of the spring forces of the previous example. We can place an insulating rod with a small metal sphere attached to both ends between the 2 electrodes of a planar capacitor as the figure shows. The rod is suspended on a low friction mounting which allows the rod to spin around its midpoint. If we charge the metal spheres with the same but opposite charges and place the apparatus in a uniform electric field E between the 2 electrodes, then it behaves as an electric dipole in the electrostatic field. The electric field represents the electrostatic force acting on the charged spheres. It accelerates the sphere with positive electric charge in the direction of the field and the sphere with negative electric charge in the opposite direction. Consequently, a force couple is exerted on the dipole with a torque which attempts to align the dipole to the straight field lines. At the same time the body starts to oscillate about its rotation axis due to the inertia of the system of the road and the spheres. It is obvious that the dipole is in equilibrium when the lines of action of the electrostatic forces equal in magnitude but opposite in direction pass through the center of rotation. In other words, the torque vanishes when the dipole is aligned to the field lines and it is at rest. If the dipole is aligned such that the spheres are closer to the electrodes having the opposite charges, then the force couple point outward from the rotation center. Any displacement of the spheres causes for the dipole to perform a damped oscillation before returning to its equilibrium position. This behavior shows that it is a stable equilibrium of the dipole. If the dipole is aligned such that the spheres are closer to the electrodes having the like charges, the dipole is still in equilibrium. However, the force couple acting on the spheres points inward to the rotation center, and any deviation of the dipole from the direction of the electric field produces a torque rotating the dipole through 180 degrees about its midpoint. Then the dipole will perform a damped oscillation before finally returning to the stable equilibrium state. This result shows that the dipole in its initial state was in an unstable equilibrium. These examples illustrate that the concept of equilibrium and its classification into stable, unstable and neutral equilibrium can be introduced for any physical system whether gravitational, harmonic or electrostatic forces acting in the system. The state of equilibrium is also an important concept in thermodynamics or statistical mechanics. We have seen that the equilibrium of rigid bodies can be stable, unstable and neutral. However, we can also test how stable is the state of equilibrium and measure its stability with different quantities. A body at rest on a horizontal surface or standing or at least three legs is in stable equilibrium, if the vertical line passing through the center of mass C of the body also passes through the surface determined by the points of support, for example the triangle determined by the support points of three legs. This condition holds for the cuboids in the first two examples shown here, but it does not hold for the inclined solid body in the third example. For the inclined body, the line of action of its weight given by its mass m times the gravitational acceleration g does not intersect the surface of support of the body. Although both the cuboids are in stable equilibrium, it is evident that the equilibrium position of the first cuboid is more stable than the one of the second cuboid. The measure of the stability for such equilibrium states can be determined by the tipping or tilting test of the given rigid body. Its geometric measure with respect to the edge E is the tipping angle alpha defined by the maximum angle through which a rigid body in a given state of stable equilibrium can be tilted without tipping over. Since the body reaches the state of unstable equilibrium closest to its original state of equilibrium at the tipping angle alpha, it is a critical angle where the center of mass C of the body is directly over the tipping edge E. The energetic measure of the stable equilibrium of a rigid body is given by the work done while the body is tilted from its stable equilibrium position about the tipping edge E through the tipping angle alpha. If the increase in the height of the center of mass C is equal to delta H, then the work W done against gravity is given by the mass m of the body, times the magnitude of the gravitational acceleration g, times delta H. The dynamic measure of the stable equilibrium of a rigid body is given by the minimum force F acting at the center of mass C with a vertical line of action that is needed to tip the body over the edge E. All the three measures show that the greater the area of the support surface and the lower the center of mass of a rigid body are, the greater the stability of the equilibrium state of the body is. An equilibrium state of small stability is also called metastable. For example, the body shown in the middle figure is in the state of metastable equilibrium. For small deviations from its vertical position the body still returns to its equilibrium position, but it is also a relatively small tipping angle. In most of the problems related to the equilibrium of a point mass or a rigid body, we can find both unconstrained and constrained forces among the forces acting in the system. The constrained forces are not predetermined, but they must be taken into account in the condition of equilibrium. We have already demonstrated that a rigid body is in equilibrium if the resultant force F of all the forces acting on the body and the net torque tau generated by these forces with respect to an arbitrary point vanish. If the forces F1, F2, ellipsis, Fn are applied on the body at the points of applications given by the position vectors R1, R2, ellipsis, Rn, then this condition is formulated by the following two equations. The vector sum of the forces Fi from I equals 1 to n is equal to 0. And the vector sum of the torques tau I produced by the forces Fi, that is the cross product of the position vector Ri of the point of application and the force Fi from I equals 1 to n vanishes. For the sake of brevity, we show only two forces F1 and F2 applied on the body at the points P1 and P2 described by the position vectors R1 and R2 with respect to an arbitrary point O, and their resultant force F. Since these equations describing the condition of equilibrium contain both unconstrained and constrained forces, it is often very complicated to solve such problems. It is especially true in the case of systems that consist of several parts, like engines or various machines. Since the condition of equilibrium must be applied for each element of a complex system, it is crucial to find a principle of mechanics free from constrained forces reducing the complexity of the problems related to the equilibrium of such systems. Let us first consider one of the simplest mechanical systems, a mathematical pendulum, and suppose that we displace it slightly either from its instantaneous position P or from its equilibrium position P0, as seen in the figure. Such a merely virtual but possible infinitesimal displacement allowed by the constraints like the thread of the pendulum is called virtual displacement and it is denoted by delta R. The infinitesimal work done along the infinitesimal displacement delta R is called virtual work and it is denoted by delta W. In the case of the mathematical pendulum, any virtual displacement can either be perpendicular to the thread as the displacements delta R1 and delta R2, or reduce the stress in the thread to zero as the displacement delta R3. Here the unconstrained force F acting on the bob is its own weight given by the mass m of the bob and the gravitational acceleration g, whereas the constrained force F' is exerted on the bob by the thread. When we studied constrained mechanical systems, we saw that the work done by constrained forces is always equal to zero because the line of action of these forces is perpendicular to the displacement of the body. In this example, the constrained force F' points from the bob towards the suspension point of the pendulum along the thread, and so, it is perpendicular to the displacements delta r1 and delta r2. In the case of the displacement delta r3, the thread is free from stress and there is no constrained force acting on the bob. Therefore, the virtual work done along the virtual displacements delta r1, delta r2 and delta r3 from the point P by the unconstrained force F is positive, 0 and negative, respectively. Similarly, the virtual work done along the virtual displacements delta r1, delta r2 and delta r3 from the equilibrium point P0 by the unconstrained force F is 0, 0 and negative, respectively. Here the unconstrained force represents gravity, and the work done by gravity is positive, 0 or negative depending on whether the displacement of the bob does not change or increase its height. This example shows that there is no virtual displacement from the equilibrium state along which the work done by unconstrained forces is positive. Another example is a lever, that is a rigid rod that can be rotated about a fixed axis O passing through the pivot point. Let the forces F1 and F2 be applied at the ends of the lever. In this case the virtual displacement is the infinitesimal rotation delta phi about the axis O, where the virtual work delta W done by the forces rotating the lever is equal to the torque generated by the forces times the infinitesimal rotation. Then the work delta W1 done by the force F1 is given by the product of the magnitude of the force F1, the length d1 of the lever arm and the infinitesimal angle of rotation delta phi. Similarly, the work delta W2 done by the force F2 is given by minus the product of the magnitude of the force F2, the length d2 of the lever arm and the infinitesimal angle of rotation delta phi. The net work done by the unconstrained forces is just the sum of delta W1 and delta W2 written as the difference between F1 times d1 and F2 times d2, times delta phi. If the lever is in equilibrium, that is the forces applied on it are in balance and the net torque generated by these forces vanishes, then F1 times d1 is equal to F2 times d2. As a result, the virtual work delta W is equal to 0. Conversely, if the virtual work delta W is equal to 0 then F1 times d1 is equal to F2 times d2, which gives a vanishing net torque. In the two examples we introduced the concept of virtual displacement with the following important properties. A virtual displacement is an imaginary displacement of a point mass or a rigid body, and not related to the external forces acting on physical objects. A real displacement would require finite time during which a point-like or rigid body might move and forces applied on it might change. By contrast, the virtual displacement of a body is a small instantaneous change in the coordinates describing the configuration of the body. It therefore occurs without the passage of time and is defined as any small displacement consistent with the constraints imposed on the motion of the body. The imaginary displacement is only assumed to exist so that various possible equilibrium positions of the body may be compared to determine the correct one. By definition, a virtual displacement conforms to the instantaneous constraints, and hence its direction is always perpendicular to the constrained forces exerted on the body. As the second example shows, virtual displacements involve not only small translations of a body but also its rotation through a small angle about a given point or axis. The instantaneous displacement of a point of a rotating body is perpendicular to the line connecting the point and the point or the axis of rotation, which is the line of applications of the constrained forces fixing the point or the axis of rotation. As a result, any displacement due to a rotation is also perpendicular to the direction of the constrained forces. Although a virtual displacement being only an imaginary and instantaneous displacement of the body is not related to any external force, we can still assume that a force is exerted on the displaced body. We therefore introduce the concept of virtual work, defined as the work done on the body by a force along its virtual displacement. If the force F is applied on a rigid body then the virtual work delta W done on the body the force along the virtual displacement delta R of the body is given by the dot product of the force F and the displacement vector delta R. The virtual work done along a virtual displacement is an imaginary quantity as well, and as the examples show, the comparison of its values computed along various virtual displacements of the body from various possible equilibrium positions helps to determine its correct equilibrium position. Since a virtual displacement is perpendicular to the line of action of the constrained forces, the work done by such forces along any virtual displacement is always zero. Then constrained forces have no role in the analysis using possible displacements of rigid bodies from equilibrium, and we only need to determine the virtual work done by the unconstrained forces acting on the displaced body. After clarifying the concept of virtual work, we can draw a conclusion from these two examples which prove to be a general condition for equilibrium. This condition is known as the principle of virtual work, formulated by Johannes Bernoulli in 1717. The principle states that a mechanical system is in equilibrium, if and only if the resultant work done by the unconstrained forces acting on the system along any virtual displacement of the system is equal to or less than zero. The principle of virtual work is one of the most insightful findings in mechanics, leading to the discovery of the law of the conservation of energy. We can interpret this principle as follows. Unconstrained forces generally do positive work, and if it is not possible to do positive work by such forces starting from a given initial state of a body or a system of bodies, then the body or the system stays at rest. The mathematical formulation of the principle of virtual work is the following. If the unconstrained forces F1, F2, ellipsis, Fn are applied on a system at the points P1, P2, ellipsis, Pn, and delta R1, delta R2, ellipsis, delta Rn are arbitrary virtual displacements of the points of applications of the forces, then the virtual work delta Wi done by the force Fi along the virtual displacement delta Ri of the points of application, can be written as the dot product of the Fi and delta Ri for I running from 1 to n. Since the net virtual work delta W done on the system is the sum of delta Wi for I equals 1 to n, the principle of virtual work can be expressed as the inequality stating that the sum of the dot product of the Fi and delta Ri for I equals 1 to n, is equal to or less than 0. In the case of many mechanical systems like a lever in the figure, for any virtual displacement delta Ri of its beam determined by the rotation angle delta phi, its opposite displacement minus delta Ri is also allowed by the constraints. Since the displacement is infinitesimal, the vectors delta r and minus delta r are tangent to the circular trajectory of the points of the rotating beam while they are opposite in direction. Both delta Ri and minus delta Ri are possible infinitesimal displacements of the beam, that is, both of them are virtual displacements. It is obvious that the virtual work done on the mechanical system must vanish, because if the work done along the displacement delta Ri was negative, then it would be positive for the displacement minus delta Ri, and vice versa. We note that D'Alembert's principle can be rephrased in a mathematical form similar to the one of the principle of virtual work. We already saw that according to D'Alembert's principle, the fundamental equation of dynamics describes the balance of the forces applied on a body and the inertial force F star given by minus the mass m of the body times the second-order time derivative of the position vector r of the body. That is, the vector sum of the forces Fi exerted on the body from I equals 1 to n, plus the inertial force F star vanishes. Then the virtual work done by the unconstrained forces Fi and the inertial force F star along the virtual displacement delta r of a body can be written as the dot product of the vector sum of the forces Fi from I equals 1 to n plus the inertial force F star, and the virtual displacement delta r, which is equal to 0. As a result, D'Alembert's principle states that the product of the vector sum of the unconstrained forces Fi from I equals 1 to n minus the mass m times the second-order derivative of the position vector r with respect to the time, and the virtual displacement delta r vanishes. In this formulation of the principle we only need to consider the unconstrained forces acting on the body, because no work is done by the constrained forces along the virtual displacement delta r. Now we present the basic mechanical devices called simple machines, which are used to do work with reduced effort and energy through a mechanical advantage. We start a more general classification of mechanical devices by dividing them into two groups. Power machines or prime movers convert some form of energy into another form of energy that is more useful for a given purpose. Power machines are, for example, hydraulic motors converting hydraulic pressure into mechanical energy, steam engines converting heat into mechanical energy, dynamos converting mechanical energy into electric generators also converting mechanical energy into electric energy, or electric motors converting electric energy into mechanical energy. The counterpart of power machines are working machines designed to perform useful work while consuming energy provided by power machines or simply muscle force. Typical examples for work machines are machine tools designed to form or cut parts made of metal or other rigid materials, cranes used to lift heavy objects or to move them horizontally, bicycles which are pedal or motor powered, two-wheeled steerable single-track vehicles, or sewing machines used to stitch materials with thread and powered by treadle or electricity. Working machines have several basic types called simple machines, which are essentially the building blocks of more complex machines. As their name shows, simple machines are mechanical devices with or without few moving parts. They are used to alter the direction and the magnitude of forces applied on them, functioning as force multipliers to do work. As a result, they reduce the effort and energy consumption through a mechanical advantage. Simple machines can be divided into two groups as well. Lever-like machines belong to the first group, whereas the second group consists of machines using inclined planes. Lever-like machines are lever, wheel and axle, and pulley, each of them used to reduce the amount of force needed to lift or lower a load. Machines using inclined plane are inclined planes or ramps also applied to reduce the force necessary to overcome the force of gravity when elevating or lowering a heavy object, wedges used for separating two objects or the parts of a single object, lifting loads, or tightening objects to hold them in place, and screws used either as a fastener to hold objects together or as a force modifier. We will discuss the different types of the simple machines in these two groups, but first we make some statements on the operation of simple machines in general. Usually, two unconstrained forces are applied on a simple machine. The first one is called the effort and represented by the force F, which can for example be a muscular force. The second force is known as the load represented by the weight G. If we neglect the friction between the parts of a simple machine or the elasticity of the parts, that is we consider them rigid bodies, then we talk about ideal machines. We will determine when ideal machines are in equilibrium under the instantaneous influence of the effort and the load. The force somewhat greater than the effort corresponding the equilibrium of the ideal machine is already enough to do the work with the machine, for example to lift a load. However, in practice we often need much greater force to do work due to the friction neglected in the case of ideal machines. Before determining the equilibrium conditions for ideal machines, we will examine some general properties of these machines. If the muscle force F1 is applied on a lever to lift a body without acceleration, then the body of weight G is directly lifted by the force F2 equal to minus the weight G of the body. The effort F2 exerted on the body by the lever is enough to overcome the load G. In this sense, we can talk about transferring force from one body to another one, here from the lever to the body placed on the beam of the lever, that is simple machines are used for transferring force. The magnitude and the direction of the input force F1 applied on the machine can be different from those of the output force F2. The practical use of simple machines already recognized in ancient times is just that a force can be used to overcome a greater load with their help. However, according to the law of conservation of energy, the work done by the output force F2 cannot be greater than the work done by the input force F1 in the same time. In other words, the useful work W2 done by the machine cannot be greater than the work W1 done on the machine by the effort. Simple machines can reduce the effort required to do the work but cannot change the work done. In order to do the same amount of work, we need apply a smaller force over a longer distance. In the case of non-ideal machines, friction must be taken into account, and the work W2 is less than the work W1 because some amount of the input force converted into frictional work instead of useful work. Then the efficiency eta of a simple machine is given by the ratio of the useful work W2 to the input work W1, which is equal to the ratio of the useful power P2 to the input power P1. In the ideal case, the efficiency eta is equal to 1, or 100%, otherwise it is always less than 1. Let us start the discussion on lever-type machines with the lever itself. A lever is simply a rigid beam that is free to rotate about an axis. Specifically, a lever transmits and modifies force or motion when forces are applied at 2 points of its beam and it turns about a third one on a fulcrum. It is used to exert a pressure or sustain a load G at one point of the beam by the application of a force or effort F at a second point turning about its axis of rotation on a fulcrum. We consider such levers where the unconstrained forces applied on the beam are only the effort F and the load G acting in the plane or planes perpendicular to the axis of rotation. Based on the positions of the lines of action of the effort F and the load G relative to the fulcrum, we distinguish three orders or classes of levers. A lever that has the fulcrum O between the lines of action of the load G and the effort F as seen in the example, is known as a first order or first class lever. In the case of a second order or second class lever, the line of action of the load G is between the fulcrum O and the line of action of the effort F, as seen in the second example. A third order or third class lever has the line of action of the effort F between the fulcrum O and the line of action of the load G, as in the case of the human forearm depicted in this figure. We have already determined the general condition of the balance of a system of forces acting on a rigid body. We demonstrated that the rigid body is in equilibrium if the vector sum of the torques produced by the forces with respect to an axis of rotation vanishes. A special case of this condition with two forces acting on a beam free to rotate was formulated by the lever principle. By applying the lever principle for all the three classes of levers, we can state that the magnitude of the effort F times the lever arm dF of the force F is equal to the magnitude of the load G times the lever arm dG, or the ratio of g to f is equal to the ratio of df to dg. This ratio, that is the ratio of the magnitude of the load or the output force produced by the lever to the magnitude to the effort or the input force applied on the lever, is called the mechanical advantage of the lever, or in generally the mechanical advantage of any simple machine. Then the lever principle shows that levers convert a small force applied over a long distance to a large force applied over a small distance. In the example illustrating second-order levers, the axis O of rotation is fixed, that is, the fulcrum is always at the end of the beam on the ground. In the case of the first-order lever shown here, the position of the axis of rotation changes along the curved crowbar with rising or lowering the right end of the crowbar. However, we can always replace the instantaneous axis of rotation with a fixed imaginary axis at a given instance of time, and determine the condition of equilibrium of the lever. In the case of the human forearm, since the bicipital muscle or biceps exerts the force F close to the axis of rotation O, the lever arm of the muscular force F is smaller than the lever arm of the load G. As a result, the effort F is much greater than the load G and our arm can move faster over a longer distance. Besides the crowbars shown in these figures, there are many other applications of the lever, such as scissors, pincers, nutcrackers, oars, wheelbarrows, railway crossing gates, various balance scales, and so on. The second type of lever-like machines is the wheel and axle. As its name shows, this simple machine consists of an axle or a cylindrical drum to which a wheel is fastened such that the wheel is concentric with the axle or the drum. Sometimes the wheel is replaced with a lever. If a force F is applied to the wheel by unwinding a rope or chain from it, then the torque produced by the force turns the axle around which another rope or chain is wound. The load G suspended from the axle can be lifted by applying a sufficient effort F. The lines of action of the effort F and the load G correspond to the tangents of the wheel of radius RF and the axle of radius RG, respectively. Let us suppose that the wheel and axle is in equilibrium, that is, the forces acting on it are balanced. Then the net torque produced by the forces F and G vanishes, and we can write that the magnitude of the force F times its lever arm RF is equal to the magnitude of the force G times its lever arm RG. That is, the ratio of G to F is equal to the ratio of RF to RG, which is greater than 1. This result shows that a wheel and axle provides a mechanical advantage equal to the ratio of the diameter of the wheel to that of the axle. Let us consider now a gear, or cogwheel, which is just a wheel and axle with teeth or cogs. In the figure we present the operation of two interlocking cogwheels, where we can see that the lever arm of the load G is given by the radius dg of the axle fastened to the driven gear of radius rg. The effort F applied on the arm fastened to the driver gear of radius Rf has the lever arm dF given by the length of the arm. Here the radii of the cogwheels are the radii of their circumferential pitch or pitch circle. Then the ratio of dF to Rf times the force F is transmitted from the driver gear to the driven one at the interlocking point. Similarly, the ratio of dg to Rg times the force G is transmitted from the greater gear to the smaller one at the interlocking point. Here the transmitted forces are tangent to the cogwheels and have opposite direction. In equilibrium, the net force exerted at the interlocking point vanishes, and we can write that the magnitude of the force F times the ratio of dF to Rf is equal to the magnitude of the force G times the ratio of dg to Rg. Then the ratio of G to F is given by the ratio of dF to dg, times the ratio of Rg to Rf. If the lever arms dg and dF are equal, then the ratio of the load to the effort is equal to the ratio of the radii of the cogwheels. Since one rotation of any gear is given by the circumference of its pitch circle, that is 2 pi times its radius, the ratio of G to F is also equal to the gear ratio, that is the ratio of the number of rotations of the driver gear to the number of rotations of the driven gear. The latter can also be expressed as the ratio of the number of teeth of the driven gear to the number of teeth of the driver gear. Then we can conclude that the mechanical advantage of interlocking gears is equal to their gear ratio. The third type of lever-like machines is the pulley used in different kinds of arrangements. The first type of arrangement is the fixed pulley seen in the figure. If we pass a rope transmitting forces over a fixed pulley, then the fixed pulley can change the direction of the line of action of the force applied on the end of the rope. In equilibrium, the magnitude of the effort F applied on one end of the rope passing over the pulley is equal to the magnitude of the load G suspended from its other end. This statement follows from the condition of the vanishing net torque produced by the forces F and G, that is the magnitude of the effort F times its lever arm R, minus the magnitude of the load G times its lever arm R is equal to 0. Here the lever arm R is given by the radius of the pulley. We can also obtain this result by applying the principle of virtual work. For the displacement delta S of the end of the rope in the direction of the force F, the height of the load G is increased by delta S if the rope cannot be stretched. Then the virtual work can be written as the magnitude of the force F times the length of delta S, minus the magnitude of the force G times the length of delta S, which must vanish. This also gives the equality of the magnitudes of F and G. A second kind of arrangements of pulleys is the movable pulley shown here. A movable pulley can be considered as a second-class lever, where the axis of rotation passes through the point O at which the rope enters the pulley. The lever arm of the effort F with respect to the point O is given by 2 times the radius r of the pulley. The lever arm of the load G with respect to the point O is equal to the radius r. Then the equilibrium condition of the vanishing net torque gives the equation stating that the magnitude of the force F times 2 times the radius r, minus the magnitude of the force G times the radius r is equal to 0. As a result, the magnitude of the effort F is given by the magnitude of the load G over 2. In other words, if the two ends of the rope wound around a movable pulley are parallel and the forces acting on the pulley are in balance, then the effort F is just the half of the load G, producing the mechanical advantage of 2. Here the weight of the pulley and the rope is included in the load G. Normally, movable pulleys are applied with fixed one, as seen in the figure. When more pulleys are combined with ropes or cables into one system, we talk about a combined pulley called a block and tackle. The block and tackle depicted in the figure consists of 2 fixed pulleys and 2 movable ones, where each pair has a common fork. Let us consider the end of the rope at the point of action of the effort F. For any displacement delta S of the end of the rope in the direction of F, the elevation of the point of action of the load G is equal to delta S over 4. Then the principle of virtual work states that the magnitude of the force F times the length of the displacement delta S, minus the magnitude of the force G times the length of the displacement delta S over 4 is equal to 0. As a result, the magnitude of the effort F is equal to the magnitude of the load G over 4, which is the force exerted on each of the 4 ropes connecting the pulleys in the block and tackle. For a block and tackle of 2 times n pulleys, the magnitude of the effort F is given by the magnitude of the load G over 2 times n in equilibrium, and its mechanical advantage is given by 2 times n. Since the effect of the friction between the ropes or cables and the pulleys increases with the number of the pulleys, there is a reasonable upper limit for the number of the pulleys applied in a block and tackle. Another type of arrangement of pulleys is the differential pulley shown here. A differential pulley is a tackle that consists of the following parts. An upper block with 2 fixed pulleys of radii R and are attached together such that they rotate about the same axis, a movable single lower pulley that carries the load G, and an endless cable or chain that passes around all the pulleys and hangs in a loop for operating the mechanism by applying the effort F on it. The fixed pulleys are toothed to avoid slippage of the chain. If the load G is applied on the movable pulley, it is also exerted on both sides of the loop. As a result, the forces F and G over 2 are applied with the lever arms R and are on the fixed pulleys turning them clockwise, and at the same time the force G over 2 is applied on the pulley of radius R turning it counterclockwise. Then the condition of the equilibrium for the vanishing net torque states that the magnitude of the force F times the radius R, plus the magnitude of the force G over 2 times the radius r, minus the magnitude of the force G over 2 times the radius R is equal to 0. By expressing the effort F from this equation, we can write it as the load G times the ratio of R minus r to 2 times R. The mechanical advantage given by the ratio of F to G is equal to 2 divided by 1 minus the ratio of the radius r to the radius R. For example, if the ratio of r to R is equal to 0.8, then the effort F can be the tenth of the load G. Now we present the simple machines using inclined planes. The first kind of them is the inclined plane itself. In the usual application of inclined planes, the line of action of the force F is either parallel with the inclined plane or it has a horizontal direction. If the direction of the force F is parallel with the inclined plane, then the condition of equilibrium is the balance of the force F and the load G representing the weight of the cart on the ramp. The force minus F exerted on the cart keeps it in equilibrium, provided minus F is the projection of the weight G on the line of action of F. Then the condition of equilibrium is given by the equation stating that the magnitude of the effort F is equal to the magnitude of the load G, times the sine of the inclination angle alpha of the ramp. If the direction of the force F is horizontal, then the condition of equilibrium demands that the projection of the effort F on the plane parallel with the inclined plane, that is F divided by sine alpha, and the projection of the weight G have the same length, but point in opposite directions. This gives the relation stating that the magnitude of the effort F times cosine alpha is equal to the magnitude of the weight G times sine alpha. As a result, the condition of equilibrium is given by the equation stating that the magnitude of the effort F is given by the magnitude of the load g times tangent alpha. These two cases show that the mechanical advantage of an inclined plane is either equal to the reciprocal of the sine of its inclination angle alpha, or the cotangent of the angle alpha. The second kind of simple machines presented here is the wedge. A wedge with a symmetric shape is made up of two inclined planes as shown here. If alpha is the wedge angle, then the inclination angle of both the inclined planes is equal to alpha over 2. Here the letters L and W denote the length of the sloping faces and the width of the blunt end of the wedge, respectively. In many applications of a wedge, for example, knife, axe, nail, pin and so on, the load is given by the forces G1 and G2 perpendicular to the sloping faces of the wedge with the same magnitude G, whereas the effort F is perpendicular to the blunt end of the wedge. In equilibrium the three forces are balanced, and the condition of equilibrium for a symmetric wedge is given by the equation stating that the magnitude of the force F is equal to 2 times the magnitude G, times the sine of the angle alpha over 2. This condition can also be derived from the fact that the effort F over 2 and the loads G1 and G2 are exerted on each inclined planes, where the effort is parallel of the base of the inclined planes and the loads are perpendicular to the inclined planes. Then the figure in the right-hand side shows that the magnitude of the force F over 2 is equal to the magnitude G times the sine of alpha over 2 in equilibrium. Since sine alpha over 2 can be expressed as the ratio of the width W of the blunt end to 2 times the length L of the sloping faces, the mechanical advantage of the symmetric wedge is equal to the ratio of the width W of its blunt end to the length L of its sloping faces. The third kind of simple machines presented here is the screw. A screw is basically an inclined plane wrapped around a cylinder to form a helical thread, as seen in the figure. For a cylinder of height h and radius r, the length of the base of the inclined plane is given by the circumference 2 pi times r of the cylinder, whereas h is the thread pitch of the screw. A typical lifting device utilizing the mechanical advantage of a screw thread is a screw jack used to lift a load by converting the rotation of a screw into vertical motion. If a load G is lifted or a body is pressed by a force G, then the line of action of the force G is the axis of the screw and the effort F is applied along the tangent to the circumference of the screw. The force G is perpendicular to the base of the inclined plane wrapped around the screw and the force F is parallel with the base. As a result, the condition of equilibrium states that the magnitude of the effort F is given by the magnitude of the force G times the tangent of the inclination angle alpha. Since the right-hand side is equal to G times the ratio of the thread pitch h to 2 pi times the radius r, the mechanical advantage of a screw jack is given by the ratio of the thread pitch of its screw to the circumference of the screw. In the case of a differential screw jack, the line of action of the force F is not the tangent to the circumference of the screw, but F is applied on the end of the jack arm of length L. As a result, the torque produced by the effort F is not given by the magnitude of F times the radius r of the screw, but the magnitude of F times the length L of the lever arm. We can apply the principle of virtual work for a differential screw jack as follows. If the effort F turning the screw rotates it by the angle delta phi, then the work done by the force F is equal to the magnitude of the F times the length L of its lever arm times the angle delta phi. The work done by the load G is equal to minus the magnitude of G times the elevation of the screw. Here the elevation is given by the thread pitch h times delta phi over 2 pi, since the elevation for a complete turn of the screw determined by the angle 2 pi is equal to h. The principle of virtual work tells us that the net work done by the forces F and G along the virtual displacement delta phi must vanish. If we factor out delta phi in the left-hand side of the equation, we obtain the equation for the condition of equilibrium stating that the mechanical advantage of a screw jack is equal to the ratio of its thread pitch h to 2 pi times the length L of the jack arm. This expression can also be written as the thread pitch h over 2 pi times the radius r, times the ratio of the radius r to the length L of the jack arm. Since the ratio of 2 pi times L to h can be chosen great enough, screw jacks can produce huge lifting force even if the friction of the screw increases with the ratio of 2 pi times r to h. For example, if the thread pitch is equal to 2 mm, the length L of the jack arm is equal to 50 cm and the efficiency of the screw jack is equal to 50%, then the load can be the ratio of 0.5 times 2 pi times 50 to 0.2 times F, that is about 800 times the effort. In the discussion on static measurement of mass we mentioned weighing scales. Now we present the measuring instruments of mass and weight in more detail. While scales and balances are both used as weighing devices, their intended purposes slightly vary. Scale measures weight whereas a balance measures mass. However, many balances are now used like scales to measure the weight of an object. Based on their working principle, there are two main classes of weighing scales, mechanical and digital. Mechanical weighing scales operate using a system of springs or levers. Spring scales and hanging scales measure weight based on the deformation of a spring due to the load. The weight of the object causes the spring to compress or stretch, and this deformation is measured to determine the weight. These scales are known for their mechanical simplicity but may lack the precision. Balance beam scales and trip scales are weighing instruments based on Archimedes' law of the lever, stating that a lever is in balance if the total torque acting on its left-hand side is equal to the total torque acting on its right-hand side. Analytical balances are extremely precise and are used to measure very small amounts of substances in labs. Digital weighing scales or balances utilize electronic components and sensors for weight measurement. They convert the force exerted by the object into an electrical signal, which is then displayed as a weight reading on a digital screen. Electronic weighing instruments can be simple digital scales or hanging scales, but their most sophisticated versions like analytical balances are used in laboratories. Digital analytical balances are generally more accurate and precise than their mechanical counterparts. Weighing devices used for commercial or laboratory use are often designated with inaccuracy classes based on the number of scale divisions. Scales in the first accuracy class are ideal for precision lab work, and have a minimum of 50,000 divisions. They display results in increments of 1 mg or better. Semi-micro and analytical balances are often rated class first. In the second accuracy class, scales have up to 100,000 divisions. Typical uses of scales in this class include laboratory weighing, weighing of precious metals and gems, and grain test scales. The third accuracy class can be divided 3 categories: medium, large and ordinary. Scales in the medium category are designed for industrial or commercial use and they have a maximum of 10,000 divisions. Scales in the large category are also used for commercial use, but they offer a much larger capacity. They also have a maximum of 10,000 divisions. Ordinary scales in the third accuracy class are used to weight heavy load but have up only to 1,200 divisions. Now we will discuss the operation of various balances and scales, where we mainly focus on mechanical instruments using the lever principle. We start with the mechanical analytical balance. An analytical balance is a measuring instrument used to determine the mass of small samples with a high degree of accuracy and precision. A mechanical version of such a balance is depicted in the figure. Its main component is a central balance beam with a sharp steel knife edge attached to the beam. The axis of rotation of the beam is determined by the contact points of the knife edge and the top of the central pillar of the device on which the edge is balanced. 2 knife edges turned upside down are balanced on both the ends of the central beam, where the axes of rotation of the knife edges can be adjusted by balancing screws. Each of the knife edges is connected to a hook and a stirrup. Bows with pans of equal masses are suspended from these hooks and can rotate about the 3 horizontal axes of rotation determined by the contact points of the 3 knife wedges. A pointer attached to the central knife wedge rotating in the front of a scale on the central pillar is used to determine the equilibrium state of the device. In order to protect the sharp edges from being bumped and the balance from disturbance, the pans can be arrested and released between measurements. The horizontal position of the balance platform can be adjusted by the leveling screws supporting the platform, and a plumb line is used to indicate when the balance is level. The analytical balance is enclosed in a glazed weighing chamber protecting the device from airflow and temperature fluctuation. Since the minimum weight is usually 1 mg in the standard weight sets, 2 pan balances are equipped with a rider made of thin wire. The variable seating of a rider on the rider bar enables smaller increments of mass than the available minimum mass to be added to the pan. Let us consider a balance with equal weights on both its pans in static equilibrium. If extra mass is added to the weight on one of the pans, then the excessive load will rotate the central beam of the balance indicated by the pointer moving in the front of the scale. The greater the angle of deflection of the pointer is produced by a given excessive load, the greater the sensitivity of the weighing balance is. The sensitivity of the balance can be described by the ratio of the angle of deflection of the pointer to the extra mass placed on the pan, or the ratio of the displacement of the pointer over the scale to the extra mass. Let us suppose that the axes of rotation determined by the positions of the 3 knife edges lie in a plane, that is, the points of rotation O1, O and O2 lie on the same line, and the 2 arms of the balance have the same length L. Let G0 and C denote the weight and the center of mass of the central beam and the pointer without the pans. The total weight of a pan and the body placed on each pan is denoted by G. For a complete symmetry of this setup, the center of mass C must lie on the vertical line passing through the point of rotation O in a stable equilibrium where the point O is above the point C with the distance d between them. If extra mass is placed on the right pan producing the excess of weight delta G applied on the right-hand side arm of the balance, then the central beam with the pointer will rotate through an angle phi and reach a new equilibrium state. Since the lever principle tells us that the torques produced for both the arms are balanced for any angle phi in equilibrium, the vector sum of the torques must vanish. The figure shows that the torque produced by the extra weight delta G with respect to the point O is given by the magnitude of delta G times the length L of the lever arm times cosine phi. Similarly, the torque produced by the weight G0 acting at the center of mass C with respect to the point O is equal to minus the magnitude of G0, times the distance d times sine phi. Then the balance equation tells us that the sum of these two expressions is equal to 0, and we can express tangent phi from this equation as the ratio of delta G times L to G0 times d. Since the extra weight delta G can be written as the extra mass m times the gravitational acceleration G, and the weight G0 as the mass m0 of the central beam and the pointer without the pans times the gravitational acceleration G, tangent phi is equal to the ratio of m times G times L to m0 times G times d, or simply as the ratio of m times L to m0 times d. For very small extra mass used in practice, the angle of rotation phi is also small and tangent phi can be approximated by phi. As a result, we can express the sensitivity given by the angle of deflection phi divided by the extra mass m as the ratio of the arms L of the balance to the mass m0 times the distance d, that is the sensitivity of an analytical balance is proportional to the length of its arms, and inversely proportional to the mass of its central bar and the distance between the axis of rotation of the bar and the center of mass of the bar. In fact, the points of rotation O1, O and O2 do not necessarily lie on a line. Therefore the sensitivity of the balance also depends on the load, and it decreases with increasing load. Now we describe how to read an analytical balance. When the balance pans are arrested, we place the sample of unknown mass on one of the pans and the sum of the weights of the weight set of known mass on the other pan. After the pans are released, the balance performs oscillations about an equilibrium position determined by the loads on the pans, which has a small damping factor due to the small friction. In order to reduce the measurement time and increase the precision of weighing, the equilibrium position is determined from the oscillation based on the theory of harmonic motion. The deflection of the pointer on the scale is read off at an arbitrary odd number of adjacent turning points after the pointer passed through the first 3 to 5 turning points. Then we take the average of the values at the left and the right turning points separately, and take the average of these two averages. For example, if the values read off are x1, x2 and x3 for 3 adjacent turning points, then the result x of the measurement is given by 1/2, times the average of the first and the third values plus the second value, that is 1/2 times the sum of x1 and x3/2, plus x2. We have seen that classical analytical balances are equal arm balances, where the torque produced by the weight of the sample on one side of the balance and the torque produced by an adjustable known weight on the other side cancel each other out in equilibrium. Then we can determine the mass of the sample from the deflection of the pointer of the balance and the known weight used for the measurement. Modern electronic laboratory balances operate on the principle of magnetic force restoration instead of the lever principle. The typical mechanism of such balances consists of electromagnetic servomotor generating a force counter the weight of a sample being measured. The main components of the servomotor are a permanent magnet producing a magnetic field and a coil supported by precision springs, which allows the coil to move in the direction of its axis. Since the direction of the current flowing in the coil and the direction of the radial magnetic field are perpendicular at all points, an electromagnetic force is exerted on the coil in the direction of its axis. This force is also applied on the sample placed on the balance pan mechanically coupled to the servomotor. An optical sensor detects the position of the coil and the sample, and provides a feedback or error signal to an electronic amplifier. When the weight of the sample and the electromagnetic force are balanced and the system is in equilibrium, the error detector is at the reference position or the null point. Then the average electric current in the servomotor coil is proportional to the electromagnetic force that is holding the sample with a given weight at the reference position. When the load applied by the sample changes, the motion of the coil is detected by the optical sensor providing the error signal, and the amplifier automatically adjusts the current to maintain the position of the coil at a reference position. The direction and magnitude of this current change are such as to restore the equilibrium condition. The electromagnetic force restoration system counters the weight exerted by the sample against the adjustable electromagnetic force exerted by the coil at a specific spatial position. By measuring the current in the coil and the electromagnetic force generated by it, we can determine the weight of the sample. Now we discuss the basic method of weighing and two other methods of double weighing. The basic method is single weighing with one stage, where the sample and the weights of known mass are balanced once. First we determine the equilibrium position x of the balance with empty pans in unloaded state. The length of left and right lever arms of the balance are denoted by L sub L and L sub R, whereas the position x is determined by the deflection angle phi of the pointer of the balance. We note that the deflection angle is not necessarily 0 for an unloaded balance. Then we place the sample of unknown mass m on one of the pans, for example on the left pan, and add a series of known weights of mass m sub r to the other pan such that the equilibrium position x of the balance could be restored. Here the subscript r indicates that the weights are placed on the right pan. Since we cannot generally combine the exact mass m sub r from a standard weigh set so that the perfect equilibrium position x could be restored even if we move the rider, we need to determine the mass m sub r by applying linear interpolation. Let us suppose that by using two different combinations of the series of weights of masses m sub 1 and m sub 2, we obtain the equilibrium position x sub 1 and x sub 2 with the original equilibrium position x between them. Then the linear interpolation gives the equation stating that the ratio of the difference between x and x sub 1 to the difference between x sub 2 and x sub 1 is equal to the ratio of the difference between m sub r and m sub 1 to the difference between m sub 2 and m sub 1. As a result, the mass m sub r can be approximated as m sub 1, plus the ratio of the difference between m sub 2 and m sub 1 to the difference between x sub 2 and x sub 1, times the difference between x and x sub 1. At the same time, the linear interpolation applied here also helps to determine the sensitivity of the balance for the given load as the ratio of the difference between x sub 2 and x sub 1 to the difference between m sub 2 and m sub 1. The torques produced by the weights of the central balance beam and the empty pans with respect to the point O of rotation cancel each other out in the equilibrium position x, and the net torque acting on the loaded balance vanishes in the same equilibrium position x as well, even if the lengths of lever arms are changed by the load. Then the net torque produced by the weight of the sample on the left pan and the weights of known mass on the right pan must also vanish, and the balance equation for this condition states the following. The mass m of the sample times the magnitude of the gravitational acceleration g times the length of the left lever arm L sub L times the cosine of the deflection angle phi, minus the mass m sub r of the weight on the right pan times the magnitude of the gravitational acceleration g times the length of the right lever arm L sub r times cosine phi is equal to 0. This equation gives the relation stating that the product of the mass m and the length L sub L is equal to the product of the mass m r and the length L sub r. As a result, the mass m of the sample can be expressed as the lever arm ratio, that is the ratio of the length L sub r of the right lever arm to the length L sub L of the left lever arm, times the total mass m sub r of the weights of known mass on the right pan. Generally, the mass m is not equal to the mass m sub r but proportional to it, where the proportionality constant is the lever arm ratio. However, we do not need to determine the lever arm ratio in many cases, for example when we prepare solutions where only the mass ratio of the components is needed. Now we discuss the methods of double weighing, or weighing of a load in two or more stages, where the sample and the weights of known mass are balanced twice or even more times. The first type of double weighing is known as Gauss's method, where the first stage of weighing seen in the first method is followed by a second stage with alternation of weights. That is, we interchange the role of the pans in the measurement by placing the sample onto the right pan and add weights of known mass to the left pan to restore the equilibrium state x obtained in the first stage of weighing. Generally, the mass m sub L of the weights on the left pan used to restore the balance is not exactly the same as the mass m sub r used in the first stage. Here the mass m sub r is also obtained by linear interpolation as seen in the first stage. Then we have two equations derived from the criterion of vanishing net torque in equilibrium for the two stages. For the first stage the original equation states that the mass m of the sample times the length L sub L of the left lever arm is equal to the mass m sub r times the length L sub r of the right lever arm. For the second stage we have the equation stating that the mass m times the length L sub r of the right lever arm is equal to the mass sub L times the length L sub L of the left lever arm. If we multiply the first equation by the second one, we can write that m squared times L sub L times L sub r is equal to m sub r times m sub L times L sub r times L sub L. Then the mass m of the sample can be written as the square root of the product of the mass m sub r and the mass m sub L, which is normally approximated as the average of the two masses. The lever arm ratio L sub L divided by L sub r can also be expressed from the ratio of the balance equations as the square root of the ratio of m sub r to m sub L. The second type of double weighing is called Borda's method, where the first stage of weighing is followed by substitution of weights, that is by replacing the sample with weights of equal total weight. In the first stage, the sample of the unknown mass is placed in one of the pans, and balanced with fine shot or sand placed in the other. The equilibrium position does not need to be the same as the one for the unloaded balance. The sample is then replaced by known weights of the total mass m0 till the equilibrium position of the balance is again established. The mass m0 is generally obtained by linear interpolation, as in the case of the single-stage weighing. Since the equilibrium position is the same for both the stages, the replacing weights represent the weight of the sample, that is, the mass m is equal to the mass m0, regardless of the lever arm ratio of the balance. Let us consider various examples for weighing scales used in everyday life. We start with platform scales, which consist of a combination of levers so that the load on one lever becomes the effort that moves the next lever. This arrangement allows a small weight to balance a heavy load. In the schematic figure of a platform scale, the lever denoted by the letters A and C at its two ends is a first-kind lever with the fulcrum at the point O. A standard weight is suspended from its end A, whereas the second-kind lever denoted by the letters H and J is suspended from its end C. The fulcrum of the second-kind lever is at its end J. Another second-kind lever denoted by the letters D and E is suspended from the right arm of the first lever at the point B with its fulcrum at the end E at rest on the lever HJ. This lever serves as the platform of the scale on which the load can be applied. In this arrangement, the following condition holds. The ratio of the distance OC to the distance OB is equal to the ratio of the distance JH to the distance JK. These ratios are constant, let us say n, even if the levers move. As a result, the platform has always a vertical displacement. For if the points B and D are lowered by the height h, then the points C and H are lowered by the height n times h, but the points K and E are lowered by the height h again. Now we can decompose the load G exerted on the platform into the parallel forces G1 and G2 acting at the points D and K, respectively. Since the line of action of the force G1 passes through the point B, we can translate the point of application of the force to the point B. By applying the lever principle, the force G2 can be replaced with the force G2 over n exerted at the point H with the lever arm n times longer than the one of the force G2. Here the force G divided by n can also be translated to the point C. If we apply the lever principle again, we can replace this force with the force n times G2 over n, that is the force G2 exerted at the point B with lever arm n times shorter than the one of the force acting at the point C. As a result, the net force applied at the point C is the vector sum of the forces G1 and G2, which is equal to the force G, regardless of where the load is placed on the platform, that is what the magnitudes of G1 and G2 are separately. In other words, we can consider the load placed on the platform as if it were suspended from the point B. Therefore, if the lever arm OA is 10 or 100 times longer than the lever arm OB, we are able to achieve balance between a body on the platform and a weight suspended from the point A that is 10 times or 100 times less than the load. After presenting scales used to weigh heavy objects, we can consider scales designed to measure the mass of very light bodies. Micro-weighing scales or microbalances operating on various principles are exceptionally precise instruments used for weighing very small samples with a high degree of accuracy. They have two basic components, electronics and another component containing the precision mechanical measuring cell. In quartz crystal microbalances, the cell has a quartz crystal, and the mass measurement is based on the observed changes to the resonance frequency of the crystal due to the addition of the sample. The cells in tapered element oscillating microbalances use a small vibrating gas tube measuring the mass concentration of aerosol particles, where the oscillation frequency of the tube changes when aerosol particles are deposited on it. Micro-weighing scales normally offer the maximum capacity between 1 mg and couple of hundred grams and readability or sensitivity down to 0.1 microgram. An important problem with high-resolution balances is related to the corrections of the buoyancy effects. The sample submerged in air is displacing air, which causes it to weigh less because the air is exerting an upward force on the sample equal to the amount air it displaced. Some microbalances offer an automatic air buoyancy correction software that ensures true mass measurement and compensation for fluctuations in air density. Another well-known example of scales is a trip scale used as a commercial weighing machine. It is an equal arm balance having pans which are flat platforms or shallow trays elevated above the beam. It has many different versions, such as the reverbal balance with two identical parallel beams mounted above a vertical column or two pivots placed in a case, as seen in the figure. On each side the horizontal beams are attached to vertical beams, and two horizontal plates are fixed on top of them. Since the vertical beams are always vertical and the plates are always horizontal, the mass of the sample placed on one of the plates is always equal to the mass of the calibrated weight added to the other plate, regardless of where the sample is placed on the plate. In the case of pendulum scales, for example the letter scale seen in the figure, the load is balanced by a pendulum moving from a vertical position representing the unload state, to a horizontal position representing the maximum weight measured by the scale. Here the torque produced by the load is in balance with the torque produced by a bob of the pendulum, where the mass of the load is determined by the position of the pendulum in the front of the calibrated scale seen on the round part of the device. Let us summarize the content of this presentation on the kinematics of rigid bodies. We started with the basic definitions characterizing the position of rigid bodies and demonstrated that freely moving rigid bodies have 6 degrees of freedom. That is, the position of a rigid body can be described by 1 point and 3 angles of rotation for its orientation. We demonstrated that the general motion of rigid bodies can be interpreted as series of infinitesimal helical motions. In other words, an arbitrary infinitesimal displacement of a rigid body can be considered as a composition of an infinitesimal translation and an infinitesimal rotation about a given axis. We also saw that special motions of rigid bodies, such as translation and rotation, can be conveniently described in coordinate representation, where the geometric transformations representing the displacement of the points of the moving body are given by translation vectors and rotation matrices. Since the effect of a force acting on a rigid body depends on its point of application, we studied how forces acting on non-point-like bodies are able to change their state of motion. We formulated the principle of superposition of forces, stating that a system of n forces acting on a rigid body can be replaced by a single force and n force couples applied on the body. We define the torque of a force acting on a rigid body with respect to a point of rotation by the cross product of the position vector of the point of application of the force, and the force. Then we presented how to reduce a system of forces exerted on a rigid body to their net force and a force couple producing a torque equal to the net torque produced by the system of forces. We define the centroid as the point of a homogeneous rigid body where the line of action of its weight always passes through. We generalize this concept to inhomogeneous bodies as the center of mass for rigid bodies, that is the average position of all the parts of the system or the body, weighted according to their masses. As we have seen, a rigid body will be in equilibrium if it is supported at its center of mass, and that the torque produced by the weight of body vanishes with respect to its center of mass. We studied the equilibrium of rigid bodies and provided the general condition stating that a rigid body is in equilibrium if the resultant force of the forces acting on the body and the net torque produced by the forces vanish. We saw that Archimedes' law of the lever is a special case of this condition. We also analyzed the stability of the equilibrium state, and gave a sketch for the proof of Lagrange-Dirichlet theorem stating the equilibrium position of a conservative mechanical system is stable if its potential energy assumes a local minimum in this position. We introduced the principle of virtual work stating that a mechanical system is in equilibrium if and only if the virtual work done by the unconstrained forces acting on the system is equal to, or less than 0. Then we could reformulate the criterion of equilibrium for rigid bodies with the help of this principle, since a system remains in equilibrium if no positive virtual work can be done on it. We studied all the simple machines, such as lever, wheel and axle, pulley, inclined plane, wedge, and screw, where we analyzed their operation based on Archimedes' law of the lever. Finally, we presented weighing scales mostly operating on the lever principle, such as analytical balances, described the measurement with balance scales, gave a brief account on the fundamental methods of single and double weighing, and enlisted some further examples like platform scales, micro-balance scales, trip scales and letter scales.